That's why I'm trying to find Mike. Mike?
Slide up.
Is he here? I haven't seen him.
I didn't know. Just Spirit. All the light years and so exciting. Oh yeah, I mean it's just such a
They're not turned on yet, no.
No. Oh, but
I have
they are charged.
But they are charged, yes.
Yes.
We have,
two.
yeah, Jens took one, and
Oh,
then,
so he's doing the
so, yeah,
oh,
what
that's fine. No.
if he wants to do it, then like, you're like, please, I don't want to do it. Yes, these are both lapel mics. Okay, hold on. Did we do
I think
PowerPoint?
just like basically like we talked about, define the box as you understand it. And I guess maybe this
Hi guys.
Hey,
Good morning.
Hi.
You made it.
Yeah. I sent my talk. I'm sure somebody grabbed it.
Yep, I have it on this computer. We're good.
hearing feedback from us about where the boxes are.
Is this, which is the slide that we want? This one or this one? This one? Hold on, Mike. I gotta get the Zoom situation
Oh my God,
working.
all of the buttons.
All of the buttons, and I'm very slow on the Windows computer.
I think that's why repetition is.
Okay, and Mike, here you go. You can.
All right.
Are you emceeing?
I think so.
Okay. Oh, yours.
Thank you. How do we get rid of that thing? All right, everybody, good morning. So we're going to get going here. A couple, well, I guess one reminder, which is if you would please mind taking a second to silence your cell phone and other beeping devices. So this morning, as we talked about yesterday, this morning into this afternoon, we're going to talk about the probes and kind of understand that parameter space a little bit better. We thought it would be instructive to have Dominic come back and present the slide on the probes from yesterday that he presented, just because some of us weren't here, but also so we can fully appreciate exactly what the box looks like that we're talking about. So I'm going to let him take it over.
Thank you, Mike. You say 3 minutes and people hear me okay? You're real quiet. I'm always a little quiet. Okay, so this is a recap of what I had said yesterday about the probe AO. Most of you probably have seen the existing community announcement that came out a couple of months ago that outlines some very simple top-level parameters. There is a draft AO in the works that will be, of course, a much longer and more complete document with a whole lot more policy stuff in it and things that you have to do to apply. A lot of it's going to be boilerplate and familiar people who've done SNEX and BidX missions before. We're anticipating that that is still going to be coming out this summer. And of course, summer goes until late September. So I think we've got enough wiggle room that it's still some time. That draft AO will be out and available for people to read and to tell us what we may have not thought of when we wrote the draft. And then there will be a final AO that goes out. The nominal planning date for that was January 2023. Because of the current planned out-year budget that comes from the fiscal 23 budget request, we are anticipating that that date is going to slide somewhat later. I don't have any prediction for how much later, but anticipate that it won't be January 2023, and therefore it'll be somewhat later, and that there will be proposals due something like 90 days after it's actually been released, which might mean that there will be a proposal due somewhere in the middle to late 2023. Somewhat speculative and big error bars on that. I have listed there in 2024, and that might still be plausible, there would be a down select to 2 or 3 that would be funded for about $5 million each to do a 9-month concept study, phase A study for the program. And that's a significant amount of investment. And we would hope that people would do a very thorough job and have a very complete program that is then assessed by our usual review process that would lead to the down selection of a single mission that would proceed to flight. Notionally in the 2025 timeframe, depending on how things go with the availability of funding, that could be 2026, but we don't want to say that. In the community, I've heard many people who have the impression that we are requiring that probe be launched by 2030. I think you can tell from the timeline I just spoke to that that isn't a plausible requirement, and so that isn't going to be a requirement. What we're picking up for now is 9 years following the initiation by releasing the draft, final AO, which would be something like middle of 2032 for launch. So that's more like the timeline we're planning for. The box that we have drawn around some top level parameters for probe is that we would have a PI managed cost cap of $1 billion in fiscal 23 money. That's not quite the same as real year dollars. You can inflate that the way you want, depending on what you think inflation is going to be for the next few years. I wouldn't want to do that myself, but you can do it. And then we can figure out there's an additional cost for the launch vehicle that's held by NASA. We'll pay for that. We don't know for sure what the launch vehicle situation is going to be. There's a procurement that happens with all of our missions that will establish what the launch vehicle is. But for planning purposes, the thing that is the right scope for a probe mission is a Falcon 9. So people can use that as a flag for now, but there may be others that are contenders by the time we actually get to the point of making that choice. There's also a Geo program, which, as is traditional for things like MidXs and SPECs, is a cost outside of the cost to the PI. So if you were to develop a probe concept that was essentially an entirely geo-based observatory, where all the telescope time was going to be established by proposal calls, solicitation for people write proposals, and they get time, the data end up in the archive, and people get funded to do the analysis of that. All that money, how to run that part of the project, that's all separate, and you don't have to worry about that. If, on the other hand, your project, your science project, the investigation that justifies your probe includes some amount of what you could call guaranteed time observations with a defined science outcome of some kind, then that would be part of the PI managed cost cap. And then there was a question about this yesterday. I think I've written that about NASA reserves. It was a various question. that the NASA reserves are above all the other reserves that the PI is going to be holding to make sure that they can meet their commitment for delivery on time and on schedule. So in a sense, you could say there's a double count of reserves, but they're there for good reasons. The PI is required to hold a certain amount of reserves and nominally have to plan for what we think of as a 50% confidence level for the likelihood of making the delivery on that a certain time, a certain schedule. NASA holds enough reserves so that we have a 70% confidence level that we will be able to, that we, NASA will be able to deliver this mission on time, on schedule. And that's the 70% confidence level. And if you've seen some slides that have been shown at various meetings for the last year or two, if you look at how many missions we have launched, that SMB has launched in the last 10 or so years since we started doing things this way, we do typically find that the average overall mission actually comes in slightly below that 70% confidence level. Not down to 50, which is where we think it should be, but that this is the amount of reserve that data seem to show is how much you actually need so that an ensemble of missions will come in at expectation. And then the other line I've got there is the quote from the decadal survey, section 7533, that talks about the kinds of science that could be included in a far-infrared probe. I've read this, I'm familiar with it, and it's pretty broad, so that we can probably find almost any kind of infrared, long wavelength infrared science in that somewhere. I think I've said everything that I had said yesterday, and do you want to take questions, or should we skip that part?
I think we should roll into the talks. Maybe we can come back to questions during the discussion period. If you haven't put on this specific.
Quick question here.
Sure, go ahead.
Dominic, is the AO going to be in the style of the Explorer?
I can say that the AO will bear substantial similarities to SPECS and VIDX faults. It's a very similar procurement process. But if you have more detailed questions, we can talk offline, and I probably don't know the answer.
Okay, so we are going to roll into a section of the workshop where we're going to hear half an hour from each of the four far-infrared probes. We're going to start with Chris Walker talking about SALTIS. So the idea here is we'll have 20 minutes or so of talking and then some questions at the end. And then we'll do two of these, take a coffee break, refresh ourselves, do two more, and then we'll have a sort of open workshop where we can discuss and ask questions of PIs or each other or whatever makes sense. Okay.
Okay, great. Can you guys hear me okay? I think that was a yes.
This is a laser pointing slide.
I don't think your mic is. All right, I think I'll have to, it's on, so I'll have to hold it up. Yeah, you just need the directional.
You can use a hand mic if you don't
Yeah,
mind.
I'll only do that.
It's a bit annoying.
So hey guys, thank you. So I'm Chris Walker from the University of Arizona, and it's nice to see the people in the brief again, a lot of old friends. It's kind of like a family reunion. I hope to talk to each of you later on today. So what I'd like to talk to you about this morning is this concept for probe mission, which we call SALTIS. Actually, John Ehrenberg came up with that name, means leap. And you'll understand why it means leap, why it might be an appropriate name for a mission like this. The words that go along with the acronym are Single Aperture Large Telescope for Universe Studies. And so, we're at the threshold of a new era now in astrophysics, thanks to James Webb's telescope. And what gives it its power is this large, cool aperture. And so we're hoping to continue that trend with SALTIS. And you can see there's lots of institutions involved. These are the main hardware providers and management. So it's led out of the University of Arizona, strategic partnerships with Northrop Grumman and NASA Goddard, many other institutions. And currently we have about 50 or so members of the science team, which are at universities and other institutions in the US and Europe. And the science team is led by Gordon Chen at Goddard. Next slide is here. Great. So here's a picture of what the SALTIS concept looks like. It looks really different from what you might be used to. So the key feature of it is a large inflatable aperture. We're going for a 20-meter class size aperture here, and I'll show more pictures of that in a minute. All this at launch, all is collapses and folds into this little bay here, and it's ejected once it gets into orbit, and then it's inflated. And I'll explain that more in a minute. And this concept is very similar for an extension of a mid-X mission, which is in process right now. In fact, we turned in the second PMWs yesterday. That's why I wasn't here, John wasn't here. Called Oasis, which is a water mission, a heterodyne water mission. And that mission features a 14-meter warm aperture, coherent spectroscopy, so a heterodyne receiver guys. So you gotta have heterodyne receivers to do the high resolution spectroscopy. It works from 0.6 millimeters to 63 microns near the O1 line. There's a nice water line around the O1 line that we're going for. And it has a 1-year baseline mission. So in terms of the probe implementation, we want to increase its power, broaden it out. Scientifically, with $1 billion budget, you can, as opposed to a $300 million mid-X proposal budget. So we're going for a 20-meter aperture, which turns out to be the sweet spot for the size of an inflatable aperture. And our Northrop Grumman, John Ehrenberg's in the audience, and the U of A team did a big exhaustive study of what's the best size for inflatable. And 20 meters is pretty much the sweet spot in terms of cost and performance. For the probe, what we'll do is we'll add a sunshade, a la James Webb, in terms of how you might achieve such a thing, which will allow the aperture to cool down to 45 Kelvin, comparable to JWST, which allows you not only to have my coherent spectroscopy type instruments, but also incoherent spectroscopy type instruments as well. And then with a mission like this, we'd like to push it to the shortest wavelengths possible. And so we're going to add some adaptive optics, some very straightforward adaptive optics to take care of any kind of weirdness that might happen in orbit and push the short wavelength of this particular mission. So we can do planetary transits. So it'll go from 1 millimeter to 3 microns. Another neat feature of it is a big antenna in space. So it's obviously could serve as a space node for EHT. We'll talk about that. And we have a 5-year baseline mission. Okay. But can it be done? That's all good, Chris, but can you really pull this off? And one thing that instills some confidence is that it's kind of been done already. This is a picture from 1996 of the inflatable aperture experiment, which actually was launched from the shuttle. This picture was taken by the shuttle astronaut. And this was a telecom antenna that's 14 meters. This isn't PowerPoint or SolidWorks. This is an actual picture of what this thing looked like in space. So over the last 25 years, the technologies needed to achieve this have improved. The material technologies, the deployment technologies, and some demonstrations, and also optics has improved. So I've been working on this particular kind of inflatable concepts. I had a NIAC in 2014, where we actually started to push the performance of these things up to near optical. So I feel pretty confident we can hit the far infrared part of it. And to demonstrate that, last year already, back in June, I think it was, John, we made a 1-meter prototype of this and put it in a space environmental chamber at Northrop Grumman and tested it, not just how it performed under vacuum, but we actually did optical metrology on it through that window by Daewoo Kim, Yuzuru Takamichi, and many students at the U of A went to this to support it. And we were able to demonstrate you could achieve the type of optical qualities you need to do a far infrared mission like this. We actually had a whole special session at the San Diego SPI meeting back in August. We have over 100 pages describing the technology behind this and the results from this measurement, so to help show that this is achievable. And we actually paid the extra dollars to make it in the public domain, so you can just download these papers. All right, so here's a block diagram. I'm going to be very speedy, so I'm not going to go through too much of it. So the basic idea is light comes in through here, hits that inflatable reflector, comes to a focus down in here. We have some corrective optics. This is all done in Code 5 by Professor Takashima at the University of Arizona. And ultimately, you end up with an F16 beam, a Gaussian beam to go into your receiver system or your instrument system, which is over here, and it's cryogenic. And here's what the instruments are. So currently, we have 4 instruments for this. We have a mid-infrared spectrometer imager, that uses mercantile telluride. It runs from 3 to 13 microns. It'll be of a grading in it. I'll show you a picture of kind of what that looks like in a minute. So we can have a spectral resolution 64 to 600. Then we'll have something we call Safari Light, but instead of the S being Spica, it's Saltus in our version of this, which is again kind of a grading spectrometer, relatively low resolution for the extragalactic stuff mostly. And then, you know, I'm a heterodyne guy, so we got to have heterodyne arrays. So we'll have a high electron bolometer heterodyne array to do high resolution spectroscopy and far infrared. And then some SIS receivers, because HEVs work great above about 1.3 terahertz. Below that, you use SIS receivers. So we have SIS receivers, and to do spectroscopy of the ISM, then we also have a receiver for the EHT. All right, so you can do lots of great stuff with a large aperture in space, obviously. And so here's actually a model spectrum of Trappist 1E that was done by Carrie Anderson. Her email's up there. So our science team is vast. We have a number of splinter groups. And at the top of these science slides, I have the leads of those groups, and I urge you to ask them all your technical questions about science questions concerning the slides, because I only have time to rapidly go through these things. But obviously, the mid-infrared is a great place to do exospheric, exoplanet science. There's a tremendous number of biosignature type lines in here. There's, of course, tons of water lines, nitrous oxide, methane, carbon dioxide, and oxygen. And so this is the kind of sensitivities we can achieve probably within one or just a couple of transits with a big 20-meter telescope, which helps to reduce the systematics associated with trying to stack up, 60 transits in order to get decent signals noise. With large aperture, you can do it all very quickly. Also, Jonathan Fortney is on this, is helping to co-lead this particular part of the team with Karen. And so there's a whole bunch of science you can do. It's really cool, right? I'm not a transit scientist, obviously, but this really enthralled me when I started reading up all this stuff you could do. Of course, you can look at all the atmospheric constituents of the many targets. We hope to do over 250 transits during the 5-year mission. And since we have such a large aperture, and we can reach the required signal noise so quickly, we can actually look for time variations in the atmospheres and not just grand averaging of what's going on. All right, so what would this instrument look like? It's mid-infrared spectroscopic imager, we call it NISI. What we want to do is copy as much of the successful heritage as possible. And a great example of this is the infrared spectrograph that was on Spitzer. And this is the paper by Jim Houck et al. 2004 that describes it. So we want to build a grading spectrometer like this with no moving parts, and basically follow this approach to achieving this type of technology, except instead of using silicon bismuth type of silicon arsenide bolometers for detectors, we're going to use mercantile telluride, which can operate at warm temperatures. Okay, of course, when you have an instrument like this, you also want to do solar system. You want to look at everything. Whenever you put a big new telescope in space, you need to go look at everything. So that's why the science team is so vast. And so here's a picture of the Earth, actually, that Carrie did this model over all the wavelengths that we would carry in far infrared. And yours has a very rich far infrared spectrum. So obviously we want to do limb sounding with that. Likewise, you could look at tons of solar system objects and do all kinds of fun stuff. You can follow the water trail into the solar system, the transport of water through the solar system, comets, look into the origin of the Earth's ocean, do deuterium ratios. All these wonderful things are enabled by having such a large aperture in space with these kind of detectors. And so over this period of time, 5 years, we can pretty much look at all the terrestrial planets, Jovian planets, and many comets as they come through the system. All right, and of course, in my astronomer hat on, I'm a protoplanetary disk kind of guy. So this particular splinter group is led by Camper Schwartz, and she put together this very nice slide to show you how, again, we can follow water through the protoplanetary disk along with other atoms and molecules. And then unlike OASIS, with SOLSTICE where we have mid-infrared, so we can also look at ICES as well and get the complete picture of planetary evolution, planet formation. All right, and then just doing astrochemistry, this group is led by Jenny Gerdner. She has a very nice paper that was recently published. And you see the little reference to it down there, where she describes what kind of science you can do with a telescope like this. Mostly that's OASIS based, but also you can do lots with the SOLSTICE. We can do the ICES as well and look into many, many aspects of chemical evolution, both in interstellar clouds, protostellar cores, and protoplanetary disks. Okay, then I'm an instrument kind of guy, if you guys know me. So I get to throw in pictures of hardware as we go. So this is a picture of the type of heterodyne array that you would use in the far infrared. This is from, about 1.5 terahertz up to about 5 terahertz. Use high electron bolometer receivers. And this is actually a picture of the flight focal plane unit, one of them, for our Gusto mission. This is actually a real thing. And it's like 40 meters by 40 meters, 40 millimeters by 40 millimeters. And you can see the little silicon lenses. And at the focus of those little silicon lenses is a spiral antenna with a high electron bolometer, micron-ish in size, 0 to the apex of that antenna. And if you do heterodyne spectroscopy, we usually describe sensitivities in terms of effective noise temperatures. And here's a list of the noise temperatures you can get. On the Gusto mixers that you just saw, we get around 760 Kelvin receiver noise temperature. The mixer noise temperature is 350. But since the Gusto mixers were made, they've gotten better by about 36%. We get around 500 Kelvin receiver noise temperature, so amazingly good. Of course, you got to do extragalactic as well with a big old telescope. And so with SOLSTICE, we can do all kinds of fun stuff. We can look at the galactic feedback from black holes and star formation, plenty of signal noise to do that. And then we can also map galaxies out to large extents out to the intergalactic medium and look at the flow of material in and out of galaxies. So the science team gave me lots of slides, so I have to go through them here. And so there's other extragalactic science you can do, of course. We can follow the trail of dust and metals like Origin was going to do. And look at the first stars in the universe. We can also look at the first stars, cosmic dawn, the first dust grains, all kinds of fun stuff. And the other thing we can do is follow up on what JWST does and find redshifts in the mid-infrared and further in the far infrared for many galaxies. These are a little plot here. We can actually look in principle all the way out to z equals 15. All right, so what would that instrument look like for the extragalactic? So here's a picture of a Safari. I just cut that out of the Safari paper from 2018 by Peter Rososima there to show you what it might look like. The main difference is that instead of using bolometer TESs, we would use MKIDs here. And one reason we can do that is because when you have a large warm telescope like ours in 45 Kelvin, the requirement of the detectors is not as great as if you have a 4 Kelvin telescope, because we have a thermal background. And so the detectors, the current MKID technology, the measured MKID performance is plenty good enough for as order of magnitude better than the background that we get from our 45 Kelvin telescope, which is compensated by the fact the telescope is so big. All right, and the last thing we'd like to try with this is to use it as a space node for the EHT. And so how would you do that? Well, there's the Earth, there's an orbit that would follow. So this would be an elliptical orbit. It would come down to around Geo, and then go up to about the distance of the Moon, 250,000 miles, 400,000 kilometers. And then we would take data as we go around when we're doing that work. And then we'd actually combine with the ground-based telescopes like the EHT does, South Pole Telescope, telescopes in Arizona, 30-meter, ALMA, to actually fill out the UV plane. So here's a picture of what you get an EHT reconstruction now, and this is the improvement you'll achieve with an instrument like this. So near Apogee, which is out there, we would actually, in this particular group is run by Dan Maroney. Oh, and Justin Spilker, I forgot to say, who's doing the extragalactic exponent group that I showed a minute ago. All right, so basically as you go out at the highest apogee, you have this baseline, and so you have the highest angular resolution, and you can use that to measure the diameters of black holes pretty much across the universe. So you can do a black hole mass census that way. Of course, because the diameter of the event horizon is directly related to the mass of the black hole. Okay, and as you're going inbound, you can make image black holes, in particular the one in the center of our galaxy, and look for photon rings, which you can use as a test of general relativity down to a pretty high precision. And then as you come closer in, we have higher signals noise and all that stuff. Then you have enough sufficient signals noise and enough you can integrate and make maps fast enough. You can actually make movies of material going around the black hole Sagittarius A and make movies of the accretion around black holes. So it's all very exciting to think about. And this is actually my last slide, which already needs to be updated apparently. But anyhow, I have the launch readiness around 2030 in flight operations in this time frame. This is pretty much the same as what Dominic showed a minute ago and be true of all the probe missions. And that's my last slide. And I hope you have a lot of questions. Thank you very much.
A runner, and then another second runner. Matt has a question.
Thanks, Chris. Very interesting. So it's a warm telescope. It's a large telescope. Can you give us a sense of what aperture efficiency do you expect at, say, 100 microns with this thing?
Yeah, so 100 microns is not so dissimilar from what we have with Oasis, and it's on the order of like 60%, so not terrible. The aperture reduces as you go to the shorter wavelengths. So by the time you get into the mid-infrared, then it's more of a light bucket type mode, which is fine for transits. We're not really trying to do imaging at that point.
Okay. And then the other 40% is just scattered to 2 pi, let's say.
Yeah, it's like typical radio telescopes have 60-70% efficiency. That's right. It just gets scattered. Yes.
And then the emissivity that you take for your sensitivity calculation?
In terms of the
warm optics emissivity total.
in terms of fractional emissivity.
Yeah, the loading basically from the 45.
Yeah. So what I did there, if you go back, actually, I use your plot. You have tons of plots like this. So if you go back, I can't remember.
Wondering if there's an actual calculation.
Yeah, there is an actual calculation. So what I did was compute the photon NEP using the classical equation that's in George Ricky's book to figure out the loading for 45 Kelvin, 20 meter aperture. And that's in the sensitivity that I can't show right now, but the sensitivity plot I had up earlier. And so basically, in terms of overall sensitivity, it's 45 Kelvin, 20 meter aperture, which is the same as JWST. And so basically for those, oh, thank you, I appreciate it.
It'll be easier to answer the question.
Yeah. It's like,
I think I know the one with the OST curves, right?
yeah, that's correct. That's it, right. Yeah, so it's just a classic picture. It's comparing to different missions. So for instance, here, all I did was scale a James Webb Space Telescope by sensitivity by the aperture of Saltons, which is about a factor of 10. And that's what moved these curves down. And then over this range, I include the emissivity in the NEP photon noise calculation. And this is where you end up on that line. This is does not include optics losses through lenses and windows and stuff. So this is likely going to be increased by factors of a few.
Right.
Yeah, that's gonna be
One
true.
of the things we did for Origins is we tried to be realistic. We based our estimates on as-built ground-based instruments of that type. And so there are some efficiencies that you want to include.
Yeah, definitely. Yeah, and so our colleagues at SRON to run those simulations now, but this is like what you can do with a 20 meter 45 Kelvin, but then it'll degrade as you include additional losses. That's right.
Good question. I'm TK from National Radio Astronomy Observatories. Thank you very much for pushing on this. I mean, 20 meter aperture can make many dreams come true, which is wonderful. And I'm also excited to see that you're pushing the far end of the far infrared into something
Right.
enabling things like black hole studies on the HT, which I'm very interested in. So I have two questions. One is, have you looked at, I'm sure you've looked at this, what about vibrations? This is an inflatable antenna, right?
Right.
And you could have, every time an antenna does something, you can have vibrations on the surface. And I'm sure you're studying this. So is that an issue? That's one question. And the other is micrometeorites and that sort of thing. So have you looked at?
Oh, we have, and John Ehrenberg, where are you here? Yeah, so let's get the phone to John. Because we just had to answer 2 potential major weaknesses yesterday about these very things. So John's over there. We can get the microphone to John and I'll let him answer those questions. This is John Ehrenberg from Northrop Grumman.
Sure. So it sounded like two questions. One was vibrations.
Yeah.
Okay, first of all, the structure is very highly damped, and for the Oasis design, we've designed all the resonances away from the resonances on moving machinery by more than a factor of 10. Your typical good practice, we can add additional damping if you like, if you're concerned about drumhead excitations in the mirror. We did do some experiments. It's not terribly sensitive to that, although of course we did them over a 1 meter a test size, not full size. So that's going to be a recurring set of measurements as we grow, and the optical design does not use the entire aperture, so there's opportunities to add damping features to the lenticular reflector. As for micrometeorites, we've done extensive testing and detailed analysis of what happens. The advantage in SALTIS is we have to have a sunshade. So this allows us to essentially do a sunshade and micrometeoroid shield. So we would expect, even though we predict with just a couple of tanks of inflated gas, more than a year or two life for Oasis, this would be extended roughly by a factor of 10 to 15, because we're limiting the solid angle of micrometeoroids to only the optical view factor, which is roughly 1/16 of the sky, and the micrometeorites themselves are not isotropically distributed. So essentially, we're going to put the armor in the direction of the big flux, and we already understand how to keep the mirror inflated. So I hope that answers your questions. If it didn't, you can find me. I'll be here till Friday.
Thank you very much.
Yeah, on the on that puncture issue, one interesting thing to remember is that what matters is the differential pressure between inside the lenticular type structure and the hard vacuum space. So when you do the calculation, the internal pressure is like a 10 to the minus 3, 10 to the minus 4 psi inside that thing. So it's like almost like a vacuum within a harder vacuum. So what happens is we poke it, it doesn't pop like a party balloon. It just slowly diffuses out. In fact, it's kind of interesting. I think we have a movie of this, John, somewhere, right? Of when we did the test in the environmental chamber in Northrop Grumman, we actually had a sewing needle and we actually punctured it. And it just sat there and it took about a few seconds and it stabilized, and the shape doesn't change at all. It doesn't pop or anything like that. And so John is actually saying we actually did tests where they actually took some of this material to light sends and blew holes through it with 200 micron pellets. And we have movies and all that to show that it can easily survive that. Right. Yeah, well, thanks.
Schultz, Sophia Institute, Stuttgart. I find this a really interesting concept and really, I mean, something really new. However, I looked at this photo that you presented, and at least in the real experiment in space that was done, there were some ripples, I think, in the fabric. So, what do you expect in terms of optical quality? What will the PSF be compared to the theoretical one?
Yeah, so the original experiment was done, it was just for X-band, basically. So it was just fine for X-band. But we've actually pushed it pretty far. I've had several NIACs on this. We've done 2-meter apertures in the lab. We've actually been able to show, measure the surface and use adaptive optics and pushed it up almost to near infrared. Yeah, I know, so it's hard to believe, but it's true. And if you look at the quality of the pictures, yeah, the big one in space is so good when you look at the picture, but if you have one of these in the lab, a modern one, it has a mirror type finish to it. It looks like you're looking at glass. And the surface RMS roughness of this material is 15 nanometers RMS as we measure. Yeah, I know, in the lab. So that tells you, if you get the optics right and take out weird aberrations with corrective optics, that says what the short waveform limit is.
Thanks.
Okay, I think there might be some more questions, but in the interest of time, we are going to move on. Thank you very much, Chris. The opportunity to ask personal questions as they arise at the end of the morning session. Jason, do you want that hand one or the bell? Okay, so our next speaker is Jason Lund, who's going to tell us about the pre-com concepts.
First question, can you hear me over the mic? How about now? How about if I use the hand mic? Is that okay?
That's fine.
Is that
That's
right?
fine.
Yep. I always
Mostly
find
for
the-
our Zoom attendees. The mics matter most for that.
Sorry about that. I always find the lapel mics kind of funny because in order for me to get them to work, I have to move like this to make sure that I don't turn my head, and I feel stiff when I do that. So I want to thank you for this opportunity to speak about PRIMA, our probe concept. This is really exciting. We started a probe concept study in 2016 with the idea that we could maybe help get a probe line created so that we could have a higher cadence of ambitious missions that could do more science than mid-axis. And I think that all the probe concept studies, and there were 9 of them that were funded, helped to make this opportunity possible. And it was kind of beyond our wildest dreams that the decadal survey would not only create a line of probes, but it would call out a competition between far infrared and X-ray. And that puts us in a really good position compared to what we've had in the past. This is an amazing opportunity. Of course, it's a really important opportunity to get right as well, because I was looking at Dominic Benford's slide that he showed yesterday, and the wedge for a far infrared flagship doesn't really open up until the early or maybe mid 2040s. And so that's an awfully long time to wait. And I think it's important for us to capitalize on this opportunity. So I'm going to focus on science for PRIMA and only talk just a little bit about technology. Matt Bradford's going to be giving a talk this afternoon where he'll talk about instruments and detectors for far infrared probes, specifically toward those with cold apertures. And he'll point out to you what's relevant to PRIMA. Of course, I can answer your questions during the question session, and you can find me today if you have more questions. So our study is a starting point is formed by the Galaxy Evolution Probe Concept Study. That concept study was very modest. We were funded at the $100,000 level. We had a tiny team, and the focus was very narrow. because of the size of that team and because we had to carry all the phase E costs in the $1 billion cost cap. Well, now that's changed because there's a $1 billion cost cap, but the guest observer program budget is held by NASA. So we have the opportunity to expand the science a lot beyond just the surveys that were designed to minimize the phase E costs for the Galaxy Evolution Probe. Our concept is a 2-meter approximately sized telescope at a temperature of about 5 Kelvin to minimize the thermal emission so that we can be astrophysically photon background limited by zodiacal light and dust from the Milky Way itself. Spectroscopy and imaging capabilities we hope to have. And I'll mention that the GEP precursor study closed under $1 billion. It was about $944 million. So it gives us a good idea of what can be done on this cost cap. I have 2 papers that you can look at if you want to learn more about the engineering of the Galaxy Evolution Probe. Of course, we're revisiting that now as we design Prima. It might be an off-axis or an on-axis telescope. We're not sure. We're doing the optimization. And the instrumentation is going to be a little more ambitious in terms of spectroscopy, but you can get some ideas. So, thank you. Okay, for future speakers, put the cursor on the slide if you're going to use the handheld. So first, who is Prima? Our core science team, and by that I mean people who are leading the science working groups and helping us lead the optimization of the science, is mostly formed, and their names are here on the left. Matt Bradford is the deputy PI and acting project scientist, and our science lead is Alex Pope from the University of Massachusetts. We're going to be having international partners on this and industry partners from the US as well. I won't say more about that at the moment. Okay, so we were really pleased when we saw section 7.553 of the decadal survey and what it called out for far-infrared probes, because our concept lined up very well with it. A far-infrared probe should do one or more of the following. It should measure the building up of galaxies, heavy elements, and interstellar dust from the first galaxies to today. It should probe the coevolution of galaxies and their supermassive black holes across cosmic time. And it should trace the astrochemical signatures of planet formation, including in our own solar system. The first 2 of these were among our goals for the Galaxy Evolution Probe, but we are expanding to do planetary formation as well with higher resolution spectroscopy in Prima. So I know that this is an infrared audience, but it's a broad audience, and I want to spend a few minutes talking about why infrared is important. There are young members of the audience present, and by the way, I was very impressed by the poise and science of the young early career speakers yesterday. So the infrared perspective is needed because of extinction by dust. So galaxies are bursty in their star formation. This is a simulation that I'm showing from a theory paper. On the right is a plot showing the log of the star formation rate versus redshift and the fraction of UV photons that escape over time or versus redshift. And the red and blue curves are 2 different halos that were followed. And you can see that the star formation is very bursty, and when it gets high, the infrared photons dominate, the UV photons don't escape, and when they do, it's during brief windows. So if you want a complete census of what's going on in the galaxies, you need to complement those ultraviolet observations with infrared ones. Okay, so what is encompassed in a mid and far infrared spectrum of a galaxy? This is a Circinus galaxy, which I'll use as an example. And you can see multiple components. 1, there's a big, bright, broad far infrared bump from the thermal dust emission. 2, there are far infrared fine structure lines Notice the range of ionization potentials here that enable you to measure cold gas, both in star-forming regions that are more quiescent and near AGN, say with the neon 5 lines. There are also broad, bright, polycyclic aromatic hydrocarbon features in the 3 to 17 or 3 to 14 micron range, and a very broad silicate absorption feature as well. These tell us about the conditions of the cold interstellar medium, the star formation rate, and the nuclear activity in galaxies, and we can use them to probe the growth of metals and dust in galaxies over time. This plot encompasses a lot. We've taken the Circinus spectrum and we've rotated it on its side, and then we've redshifted it so that you can see these spectral constituents and when they show up in the prima band as a function of time or as a function of redshift. By looking at the various colors, you see that the cold interstellar medium associated with star formation and AGN and warm molecular gas have multiple probes present at most redshifts. The polycyclic aromatic hydrocarbons start coming into our bands at very low redshift as well. The red arrow, the vertical arrow, indicates the prima range. The lower gray range is JWST, and the upper gray range is ALMA. The ALMA observations, or the ALMA range here isn't quite right. It goes down to 400 microns here, but it actually should go down almost to 300 microns. Prima, we know our spectral coverage will start around 24 microns, overlapping just a little bit with JWST, and it will run out either to 200 or 300 microns approximately, depending on our optimization. So we'll cover all that range, perhaps concurrently with JWST and ALMA. Instead of trying to follow all those lines on the plot, I've picked a few from a table here that shows the redshift range and sort of approximate brightnesses of the features. The polycyclic aromatic hydrocarbons for a spectrometer will start coming into our redshift range at about 0.8 and essentially go to the highest redshift that we can see polycyclic aromatic hydrocarbons. These features are very rich. They tell you a lot about galaxies, and they seem to be present at high redshift. I've highlighted in red lines that indicate nuclear activity, accretion on a supermassive black hole. And we start detecting those at low redshift as well, and we can see them are at 0, in fact, all the way out to a redshift of 7. We can see bright oxygen 4 line all the way out to a redshift of 6.5, and the brighter low ionization oxygen lines out to past or before cosmic noon. So how do our science goals line up with what the decadal recommends? Well, one of the things that we want to do is measure the growth of metals in galaxies over cosmic time. It's important to complement the optical, rest frame optical and ultraviolet observations with the far infrared, because the far infrared has extinction-free probes, and you can see right into the disks of galaxies where a lot of the interstellar medium is. Furthermore, the temperature and ionization degeneracies in the optical, rest frame optical lines can be avoided. So this plot shows the log of metallicity on the vertical axis and on the redshift on the bottom horizontal axis and the age of the universe on the vertical axis. There is a compilation from Medow and Dickinson 2014 of various metallicity measurements. There's dispersion in there, and there's a cosmic average expectation, and there's a lot of dispersion. That's not really the point. The point is, in the upper left part of the diagram shown in gray is the redshift range that Prima will probe with its metallicity measurements. And you can see it ranges all the way from about 2.5 billion years after the Big Bang to the present day, which means we can probe when most of the stellar mass in galaxies was built up and the interstellar medium was enriched. How would we do that? Well, 2 examples are using the ratios of oxygen to nitrogen and sulfur to neon. At lower redshifts, this works because oxygen is a primary stellar nucleosynthesis process, but nitrogen is secondary, meaning it is formed both in the cores of stars, but also in the shells later on. And so you can form a ratio between these two that changes as a function of stellar processing, which is a proxy for metallicity. And then you can calibrate it against other metallicity indicators. And that's what's shown on the plot from the left by J.D. Smith. And in fact, the oxygen to nitrogen ratio only has a dispersion of about 0.1 DAX. So this will allow us to probe almost out to cosmic noon. Then at higher redshifts, we can use the sulfur to neon. The reason is that neon is inert. It remains in the interstellar medium. Sulfur, by contrast, gets partially depleted onto grains. So it grows less than linearly with metallicity. So you can form a ratio between these two lines, and that's been calibrated with 47 galaxies in the local universe from Spitzer, and use that to measure metallicity as well. Okay, another goal is to probe the coevolution of supermassive black holes and the growth of stellar mass in galaxies. I like to start with this plot from 2000. There are many more data points now that show the correlation between supermassive black hole mass and bulge stellar velocity. But I like this one because it was original. It's the original, and it was very exciting when it came out because it raised the question, how can two processes with such vastly different size scales be related to each other? Obviously, they are related. So what can we do in terms of understanding this? Well, we want to understand feedback in galaxies, and we want to measure which feedback likely regulates both the formation of supermassive black holes and stars, and the dispersion between the formation rates of the supermassive black holes and the stars over cosmic history. In the original GEP version, we had an imager that had very narrow spectral bands for an imager in the mid and near far infrared, with a spectral resolving power of about 20 enabled by a linear variable filter running from 10 microns up to 26, and then narrowband filters from 26 microns out to 100, and then beyond 100, much wider ones. What's shown on this plot is the spectrum, model spectrum of a galaxy from Danny Dale with far infrared dust emission, polycyclic aromatic hydrocarbons, and that silicate absorption. And the idea was to survey for the sky for many galaxies, measure their redshifts using the polycyclic aromatic hydrocarbon features and their far infrared luminosities, and use the mid-infrared spectra to distinguish the star formation from the nuclear activity. Our simulations showed that we could get sigma z over 1 plus z as good as 1%. And it was limited by the dispersion in the polycyclic aromatic hydrocarbons from I feel that way every time I think about polycyclic aromatic hydrocarbons. I'm so glad. So I was a professor here for 20 years. I have a feeling that was one of my former students getting some revenge. And right. So I lost my train of thought, although I enjoyed that. So the idea was to do a lot of surveying and detect many galaxies, measure the redshifts, separate the AGN from the star formation. And then we ask a question, can you use the mid-infrared spectra without spectral lines to distinguish the AGN fraction of the bolometric luminosity? And the answer is yes, you can do a really good job of it. You can measure the AGN luminosity fraction to about 10% because the AGN heats the dust more in the mid-infrared and makes the spectrum bluer. It also suppresses the polycyclic aromatic hydrocarbons because the continuum comes up from the warm dust. So this is really exciting because it means we could do it for many galaxies over many epochs. Of course, if you add in the far infrared fine structural lines, then you have another measure of the AGN accretion rates. So what about feedback? Well, we need higher spectral resolving power than R of a few hundred, which is what we imagined in our initial study. In fact, you need a resolving power of a few thousand. So what we anticipate doing is taking our grading spectrometers and putting either a Fourier transform spectrometer in the beam path in front of them, or embedding Fabry-Pros with the diffraction gratings in order to get higher spectral resolving power. We're doing an optimization now to figure out which one of those schemes is most efficient for us and gets us the most science. Here's an example of what you can do with outflows. So we would observe many high J carbon monoxide lines in the far infrared spectra of galaxies. This is lower J lines of carbon monoxide towards a massive starburst galaxy at a redshift of 1.4. It's actually an extraordinary galaxy. The main cores of the lines are sort of on the left of a very broad peak in each case that you see, which indicates the outflow. It looks like it's ejecting something like 46% of its molecular gas at a rate of 10 to the 4 solar masses per year, which could be polluting the circumgalactic medium with the metals that we see in absorption lines in the halos. And in fact, it suggests that the merger-driven episodic events are bursty rather than steady state, and that's what's quenching star formation. And that's consistent with the model the theoretical model that I showed earlier. You need a resolving power of a few thousand to measure those velocities and then to determine the mass outflow rates and determine the energetics. So that's what's driving us. We're also moving into origins of planetary systems and particularly water transport to the habitable zone. This requires a spectral resolving power in the 3,000 to 5,000 range, probably closer to 5,000. But you can survey hundreds of disks with a cold 2-meter telescope. There's sufficient sensitivity to do this. Shown here is a plot generated by Klaus Pontoppidan, showing the spectrum of a protoplanetary disk where there's dust emission. Superimposed on that is a plethora of water lines, and then shown in blue, solid state features of water ice as well. And then there are silicates towards the mid-infrared part of the spectrum, or the short far infrared. By modeling this spectral energy line distribution of the water, which is subject to many temperatures, you can determine the distribution of the water in the disk, and you can compare that with the ice as well. And you can use it to study the evolution, the location of the water in the disk and its evolution from over time by comparing systems when you survey hundreds of them by measuring their stellar ages. There's another important measurement that needs to be made, and that's the mass in the disk itself. It's largely unknown, and the uncertainty is probably an order of magnitude in disk measurements, because the carbon monoxide abundance is not well known. It's probably uncertain to a factor of 10, and there's dust depletion. So there's a way to solve this problem, and that's using an optically thin line. And the HD 1-to-0 line at 112 microns enables us to measure masses in that way. So we're in the process now of doing an optimization between sensitivity and spectral resolving power to figure out what is optimum and comparing this to the other science cases. So the Galaxy Evolution probe showed what we could fit in the budget. And we think it's a cold 2-meter telescope. And by cold, I mean 4 Kelvin. So we're astrophysically photon background limited. And we can have 1 or 2 ambitious instruments. And that would mean, for example, a spectrometer from 24 to 200 or 300 microns with a resolving power of a couple hundred, plus a resolution of a few thousand or maybe a little bit more from insertable high resolution modules. You can potentially also fit an imager of the type that I described. And you can even maybe make that into a polarimeter, because the detectors that we're looking at are inherently polarization sensitive. And so you sort of get that for free, not quite for free, because you reduce your noise equivalent power, or you raise it about a factor of square root of 2. But it may be by gaining that polarimetric capability, you win out over the loss in sensitivity, especially because the telescope is going to be extremely sensitive and fast. The detectors that we're baselining are kinetic inductance detectors with on the order of 25,000 detectors in each of the instruments, maybe fewer in the imager. And we're pursuing partnerships on building the imager because up to 1/3 of the cost can be from foreign international contributions. So Matt Bradford will talk more about this technology and its readiness and the advances that we need to make later this afternoon. That's relevant to many of the probes. So how much time? How much time do I have left? 5. Okay, excellent. So I'll finish up very quickly here. So we're clearly very excited about Prima, and we were also happy when we saw the call that would enable it to have a large guest observer program. In fact, much larger than the likely guaranteed time fraction of it. So we opened up to the community right away. We started building our science team. The core is now over a dozen people. The working groups total several times that, people who are bringing science cases to us. We opened a community survey in which we ask people, what capabilities do you think a far-infrared probe needs to have within the envelope of what we think we could fit to help us optimize? And what are the science cases that you would use the telescope for? So we ended up getting actually 125, I think, responses so far in this survey, which was really exciting for us. There's a broad range of input. In fact, approximately half came from the United States and half came from outside the United States on this. And it was a range of institutions from observatories and government labs to universities. There was a strong demand for almost everything that we asked for, including, or that we said we could potentially provide. RF 200 spectral resolving power spectroscopy, higher resolving power spectroscopy in the range of 10 to the 3 to 10 to the 4, broadband imaging with the high resolving power imager, and polarimetry, if we can make that happen. Furthermore, there was a broad range of wavelengths that people were interested in, from 10 to either 200 or 300 microns, but really there was a peak in the 25 to 200 micron range. We presented these results to the community at a workshop that we held on March 22nd. And there were 175 participants in this virtual workshop. And there were discussion sections just like we've been having here, and it was really rich and helpful. One area that we thought we needed to improve, though, is on this pie chart on the bottom, where we see the early career people who contributed science cases is shown in the sort of brown-orange color, which is postdoc, which is where the arrow terminates, and then graduate students, which was the thinner cyan wedge. We think that there's a barrier for young people to contribute science ideas because they think that they might be judged, or maybe they're not equipped, but there's a lot of creativity that comes from early career scientists. So we created a special workshop, mentoring, where 4 of us were present and about 20 early career scientists, postdoc and graduate students, asked us questions and then helped formulate their own science cases. And so we got about 20 of those. It's one area we want to continue to grow because it's going to be 2032 by the time this thing flies. So with that, I want to say, contact us if you want to get involved, or we'll still be accepting ideas. And if you get a picture of this QR code, you can get on our email list and get semi-regular updates of what we're doing with our project. Thank you.
Right. Thank you, Jason. Any questions?
Is there any chance we'll push this to a larger dish, or is 2 meters really the limit that is possible?
Okay, so that's a good question. Is there any possibility of pushing this to a larger telescope primary mirror? Is 2 meters the limit? So we're asking that question right now. And we're looking at the cost implications and implications on axis versus off axis. If we wanted to make it larger, we'd have to make it on axis. And the question is, does that change the structure so much that it becomes too expensive to fit in the cost cap? We don't have the answer yet, but I think the upper limit on the diameter that could possibly be achieved is about 3 meters. We may not do that because we want to make sure we have enough instrumentation capability, because that's important too.
Thank you for that nice overview of your project. You've steered clear of heterodyne instrumentation on this, right? So is it because you cannot fit in so many instruments within the cost cap, mass cap, and all that? Or you don't find sufficiently strong science cases for heterodyne?
Okay, so the question was, in case you didn't hear it, we haven't included heterodyne instruments in our observatory. And what is the reason for that? Is it because of the cost cap or are there science reasons? So the answer is the cost cap. If we could fit more instrumentation, we definitely want to do that. But we have to optimize with what we think we can fit into the budget. And we think the instruments that we've selected here have the highest science appeal that enable us to drill down and are broad. Also, with a small, if I can say 2 meter telescope, that's bigger than me, telescope that's cold, we don't think that it fully gives you the advantage that you can from a heterodyne receiver, which is quantum noise limited. The direct detection receivers really benefit from the cold telescope.
Well, if there are no other questions, I propose we take our coffee break. And we can think of questions and ask Jason. Let's reconvene at 10:25. We're good. Not one of those. Click on view, full screen.
I am aware. I was not the one that messed it up.
Hide floating unit controls. Click. Okay, there.
But now you gotta click that.
Just gonna test it. Where's that dancer? What has it signed?
Did Jason take it?
I should do a sign filter. So what's the deal with
No, it's not
airlines?
this guy.
Yeah.
It'll work. It's fine.
I yelled. Okay, everybody, let's take our seats. Wrap up our combos. Yeah. Okay, so we're going to start the session, or continue the session, I should say. With second two probe concept talks, and then we have about an hour to discuss and ask questions and have thoughts. And then we're going to take everybody outside and take a group photo against the mountains. So please don't run off the bunch of I think we're in a situation where everybody stopped talking except for Bernard and Gary. when pointing out. Thank you. Okay, so our next talk in the series from Asanta Kure, and he will tell us about the first concept.
All right, good afternoon. Can you guys hear me? Good morning. It's good to be talking to all of you. All right, so I'm gonna throw in another idea to the hat in terms of probes. So to set this off, this might be confusing, so I'll explain this. It's a plot. Wavelength, y-axis, spectral resolving power on the x. So, you know, things which are like out of 1, 2, 3, those are broadband imaging of the sky that are in the medium infrared to far infrared wavelengths. So those are kind of useful for like galaxy imaging surveys, mapping the Milky Way polarization, right? So kind of, you know, science related to that. And not to like, you know, make it seem small or anything, but it's really medium infrared. So my scale is medium, you know, linear. You guys can hear me?
Yeah.
Okay. All right, so my wavelength is in linear. So medium infrared, you know, the range of like 1 to 30 microns is kind of small in here. Exoplanets, you know, doing amazing lot of work there, right? Spectroscopy of exoplanets. So you don't really want to be down here out of 1 to 3. We are really talking about out of 10 to 1. All right, so let's keep on going. Really high spectral resolving power. We are talking about sub-kilometers per second velocity measurements in the Milky Way, planet-forming disks, star-forming regions, protostellar poles, right? You really want to go after key spectral lines. So we heard about all of that, right? The water lines. So there's a whole series of water lines in here. There's all the other lines, right? Oxygen, nitrogen, HD, HGO, things like that. So they capture different kind of science. So planet formation down here, maybe some sort of a star formation, interstellar medium, some kind of connection here. Planetary habitability, that's just like, you know, water transport paths out there. Okay, so we have a phase space, and you can ask questions like, how do I get to this phase space with $1 billion, right? So remember, this number hasn't, maybe it has been said, but you really have to think about it, like what can you do with $1 billion to cover this phase space? So we heard about 2 options, right? And there's probably more, but anyway, so you can go after, on this end, you can have a pole telescope, right? SOFIA is 2.5 meters. So ideally you want to be at least SOFIA or SOFIA plus. So 3 meters perhaps, 4 Kelvin class, 4 Kelvin cold. And you can fill it up with the imaging cameras, and you can fill it up with low resolution spectroscopy. And that's probably $1 billion right there. Okay, so you can concentrate mostly on galaxy formation in that way. These are not, you know, none of these are great, correct answers to this problem. And I'm not saying none of these are wrong answers. And then you can do the other thing, and you can go after heterodyne technologies, sub-kilometers per second resolution spectroscopy with a large telescope, like a 10-meter class, right? Whether it's 10, 20, 30, it doesn't matter, right? It's just that level of size. But you really cannot, you have to do passive cooling because you have to save the budget cost, you know, cooling against something else, perhaps. Okay. So we thought about this, rolling a bit, and said, is there something else we can try? At least, you know, give it a try. How can we approach this? And can we push it through? So we want to do somewhere in the middle, okay? Something in between. So it's really spectroscopy that I'm going to be talking about. So we have to drop this end. We have to go to the long wavelength end and capture as much of this phase space as possible with the instruments. So that's where we are. So it's a simple idea. We're thinking very simple. Even our name is very simple. It's a fine-infrared spectroscopy space telescope. So the idea is to figure out in the sort of the way Spitzer was built. Spitzer was a simple mission, right? 85-centimeter telescope. Did amazing science. So can we do something like, can we recreate something like that to allow community use? So 100% community geo. So there's a small GTO just like Spitzer had, or just like James Webb will have. And can we capture most of the science from the studies we've done in recent years, like origins and all the other ideas up there? That's a large team. Perhaps the things you want to know is just like missions we heard about, led at JPL, and we're going to hear about Goddard missions. Well, we heard about one. This is led at APL. That's associated with Johns Hopkins. So they're going to be the representing the community. We have industry partners, we have NASA partners, and perhaps partners from outside US. The science team is broad. We are covering all aspects in the community, diversity of science, diversity of people. You can anywhere you want to break that phase space, and then we welcome additional members. This is really what I can show right now in terms of the way we are thinking about how to put this team together. So this builds on, perhaps on the other end, the origins. It's a large telescope, very ambitious science case. In fact, the origin story starts with a 15-meter telescope. That was our concept one. And that was like $35 billion to set the stage for scaling. Anyway, so on the right hand, there's speaker, right? 2.5, 2.2 meters. So that's where we are thinking, go ahead, stuff like that. Perhaps a plot. This was in the origin study. I'm just putting it back again. So this wavelength range, right? We really had to go outside the atmosphere. We knew that. Preaching the choir here, so probably don't need to. But in the fine infrared, right, we capture processes, molecular processes. We capture stars, atoms, all of that, right? So it's very unique. It's not like in the optical, where you're trying to deal with like atoms and ions, or going to the radio, where you're mostly dealing with like molecules, right? So, and then we see the dust emission. So there's unique ways to use that scientific information to understand what's going on in the universe that we haven't quite explored, right? But we do have problems, right? I mean, we work in the long wavelength, diffraction, diffraction is large. So people are going to get used to, people are used to the point space function of Hubble. They're going to get used to the James Webb. We really cannot recreate that, right? So, but we can, we can do other stuff that are unique to us. So we have a fact sheet. It will show up somewhere, and it's going to be online. We'll pass it around over email to the email list too. So we have top 3 science goals. So in terms of understanding planet formation, habitability, all of those unique questions, we want to understand the origin and the evolution of planet-forming disks. And then, for our science case, and I think the community will be interested too, a unique case to go to space. Like we are not limited by balloons or like Sophia, is the atmospheric water, right? So you really have to get above the atmosphere. So really a unique reason to go to space is the water. So understanding the trail of water from molecular clouds to the oceans today on Earth, that's what we are after. So Meredith will talk about this in the afternoon, these two. I'll quickly touch on, you heard about quite a bit of this stuff too. How do galaxies assemble their material? That's our kind of level 0 science goal. So I'll put this as a glance, and we come back to this at the end too. So you've seen versions of this. So 2 instruments, all focused on spectroscopy. A low resolution mode, a high resolution mode, and then heterodyne. And it's a 2-meter class telescope, blah, 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 right? That's really what I can say right now. So let's go to the extragalactic stuff, right? So as I already said, fine Fred is rich in spectral lines. This is almost all of the fine Fred spectroscopy data we have right now. It's 200 some galaxies from Herschel, and there's some ISO data. Everything's stacked together into a single spectrum. You can see, CO lines, water lines, carbon-2 popping up, oxygen-1, things like that. So we know how widely use these things, right? Yeah, assembling material, right? So, we want to understand how gas flows in, how gas flows out, how gas gets converted into stars, the explosions, the feedback, the supernovae explosions, it's a very long cycle, right? And that can be captured in many lines, right? There are these spectral lines in the fine Fred carry information on AGNs, the stars, metals, metal processing galaxies. So line ratios tell you crucial things, right? There's going to be an amazing amount of work in the coming 10 years, right? From James Webb, especially in this mid-infrared. And what we'll be doing is, using those techniques developed by James Webb and applying them at higher redshift, maybe like Redshift 2, where the wavelength drops off. So we want to address things like, so within that theme, galaxies assemble their material. We want to understand things like, how is like gas, metals, dust flow into, through, and out of galaxies? How do star-forming structures arise, interact with the ISM, role of central supermassive black holes, things like that. Here's another way to think about this. So I've shown this many times before in my talks. So back in '87, right, the community had like 100 galaxies in the optical. There was a transformation from Sloan survey where they could do these statistics for like millions of galaxies, right? And I said, like in the fine Fred, mid-infrared, we are dealing with statistics like 100 galaxies where we can do this line ratio measurements. So, a good scaling for us would be in 10 years with a facility like first, get statistics, all this, 5 years of programs, community will do, capture that to the level of like thousands of galaxies, right? Understanding what's going on. So it's not completely blind. We can do a little bit of things with SOFIA, which you've been doing. So Herschel pack started at like 55 microns. This oxygen 3 line at 52 microns is kind of crucial for a lot of stuff. But then the SOFIA has an instrument that can get this line for nearby galaxies. And it turned out it's even for nearby galaxies, these are really bright ULERs. It's not easy, even with SOFIA. It takes so much time, multiple cycles, multiple flights, to even build up like statistics for like 5 galaxies to get enough data. But that's where we are, right? That's what we have to get used to. Yeah, so we have PEP coming out where we see this oxygen line, and we can use the oxygen line with packs, the 88, oxygen 3, and some of the nitrogen lines like the 57 micron to measure like metal abundances. And we kind of solve the problem that my postdoc, he'll have a Nature astronomy paper coming out in 2 months that accepted in press, where we showed like, solve this problem with like low metal abundances, ULERs, with SOFIA oxygen 3 and new nitrogen 2 measurements at 57 microns. They are consistent with like Sloan galaxies. And then with first, we want to push these kind of things to higher redshifts, right? So we are not limited by sensitivities. We are trying to improve by factor of 30 or 50 these sensitivities from a space telescope. So yeah, so we can go after like, high redshift galaxies. We know lots of galaxies, right? That ULERG-like or even HILERG-like, thanks to Herschel. Herschel did amazing imaging. There's like 1,200 square degrees. There are thousands of samples that anybody can go after. So the idea is, we will follow them up. We only managed to follow up maybe like 10. Like, I can name these galaxies that Herschel did good spectroscopy with my fingers, but, we really want to be following up large samples. Here's an example of a spectrum with Herschel, just that carbon 2. So depending on how this instrument is constructed, in first, we can maybe a slit, we can scan the sky, map nearby galaxies. There's interesting science we can do, tracing gas, diffuse emission that captures that outflows like supernovae-driven winds, so AGN-driven winds, things like that. Which is, we can think about that in the way. There's an interesting project in the local university that Sloan is doing. It's called Manga, which is they stack all the fibers together, and then they can do spectroscopy for all of the nearby galaxies, thousands of galaxies. So we want to do that kind of stuff, right? Even though our beam is large, we should still be able to do resolve spectroscopy. The order of like, a few hundred galaxies in the nearby universe. And then the question becomes, why do you want to do that? Why are they useful? So on this question of like how gas flowing out, like gas getting thrown away, a supernovae maybe, shocks throwing gas, black holes, winds throwing gas out. And we kind of seen that stuff. And you can go after this like unique P-Cygni type profiles. Yeah, you see the gas redshifted and blue shifted and soft. Herschel did quite a bit of that. This velocity widths are humongous. Right, so even high five saw one of these lines in nearby galaxy. So the science case can be extended to higher redshift with a facility that's really unique. The issue with Herschel was 70 Kelvin, warm telescope, right? You really have, then we can connect our science case, at redshift of 1 to like what's going on with ALMA. So at like redshift of 6, 7, 8, ALMA is doing amazing work, like carbon 2 line at like redshift of 6 in some of these, high redshift galaxies, and they see this broad emission, like 3,000 kilometers per second, outflowing from galaxies. Spire saw that one nearby, like, level of like 1,000 kilometers per second. So yeah, so I grabbed this from the speaker study. So these outflows in OH, right? You need moderate resolution spectroscopy, R of like few thousand. So we have a mode, a high resolving mode that's really designed to do science for the two cases that I didn't discuss, protoplanetary disk or the water, things like that. But those bands will overlap with redshift windows for extragalactic sources. So you can go after, so there are broad redshift windows where we can do amazingly high resolution spectroscopy. Not just see these massive outflows from black holes, but these low level outflows from like supernovae. The velocities of like 600, 700 kilometers per second. Not this, the 3,000 kilometers per second, we can even see it without, the broadband spectroscopy. All right, so the idea is like, you want to be doing something new that doesn't sort of like, limit your ability to do science or limit the ability of future generation to do this science in like 10 years, right? So I think I've shown this before. This was an idea that Gary convinced me. So that, every time our community has done a telescope and put it to space, IR picks the Herschel, amazing discoveries have been made that weren't discussed or thought about at the time of like writing the proposal or like building the instrument. And they all worked out great because the instruments weren't limited, had the capacity to make additional observations. So, it was not, it wasn't focused on like answering one or two things. Perhaps it was designed to answer one or two things, but had the opportunity to do a lot. So yeah, like I think like amazing result that came from Herschel that probably we don't appreciate. Water lines exist. Water cooling in galaxies is amazingly comparable to like CO cooling. even all the way out to like, reionization of first galaxies, right? There's this galaxy ratio 6.3. Most of the brightest lines are just water cooled in that galaxy. So I think even in the extragalactic, even though we think about water in our own galaxy and the transport to make like the oceans, yeah, so we'll think about some of that stuff going forward. And there's all the other stuff that, can get done, that community can use this for. So I said, yeah, I'll lend this back again. So with putting this spectroscopy focused, that is not to say you can do spectroscopy and collapse in the wavelength direction to make images, right? So there's a technique, IFU, you can collapse the wavelength and make images on the sky, but we do not have a dedicated imaging camera. There's really no need, we think, to do that, but here we are. That's my talk.
Thanks, Asaf. So you said in between, you are planning to cool the telescope though?
Yeah, it's a cryogenically cooled.
Okay, so you're targeting 4 Kelvin. The sensitivities are based on a 4 Kelvin, I guess, right?
It's somewhere there.
So something cold.
It is cold, actively cold.
You might have said this, but what are the instrument complements that you envision for this?
Right now it's 2 instruments, a vocal, so like a direct detection, 2-mode instrument that has low resolution broadband spectroscopy, just like Safari Mini or something like that. And then high resolving power infinite band, 10% band, you say. And then a heterodyne at a long wavelength.
So the heterodyne just mentioned, 600 micron. And if you can make your antenna a little bit bigger, I don't know, that's still not decided, right? You said 2 meter class, maybe 2 meter, whatever. Then it would bring black hole studies with VLBI into picture with ALMA. The baseline can be
You don't think a 2 meter telescope is enough?
I mean, yeah, a 3 meter telescope, for example. Yeah, I mean, yeah, you can cover any additional very exciting science space. Possibility to think about.
Since it's a geo-based observatory, it's pretty much pointed science, but there could also be surveys. So are you thinking of the telescope being agile enough to do survey modes, or is it just you want to stare and then move and stare and then move? Is the design sufficient to do 2 different types of looking at the whole sky and staring at one place?
So it's let's say it's point source spectroscopy, but then it'll have it won't be able to survey hundreds of square degrees. It will have mapping capability to do like small areas.
Honestly, I see you have a question, but I think in the interest of time, maybe we'll hold it to the discussion. We have plenty of time. That's what she was trying to say. Go ahead. Sorry.
Yeah, I have a question about the band for the heterodyne receiver, because I mean, from Atacama, I guess with CCAT, you probably can access a lot of that band. Obviously, the ground state waterline is there, but there's another ground state waterline at 170 something microns, which I think would give you a lot of information. So I see a big overlap actually in the heterodyne band with what you can do from the ground, aside from the water.
Yeah, probably. Gary has something to put on that. So.
This is as much a question as an assertion, but in the non-seriously Doppler shifted case, I was surprised that you convert at 270 microns, which is the ground state line of parawater, even from at a common. And certainly you can't do it at 538 microns by a long shot. 179 for the atmospheric transmission of the. But I thought you were saying this could be done from the ground. No. Oh, sorry. I misunderstood.
I was wondering why I can do that and fix food potentially.
Oh, well, that may be done by the heterodyne. And then, I think that's up for discussion. I'll just comment also, with regard to using these probes as a node in the Event Horizon Telescope, that was an idea I had for Origins originally, and submitted a white paper on that to the decadal. And it is an intriguing idea, so much so that I thought Origins would do it. But one has to note that it doesn't come for free, in the sense that, as with any node in an interferometer, you need very, very precise clocks. You probably a factor of 10 higher in precision than anything that's been flown to date. It's not to say in 10 years it won't be possible, but you also accumulate huge amounts of data in a very short time. So your onboard storage requirements are enormous. And you also have to know the position of your spacecraft to, better than a centimeter. When you're doing interferometry, it's essential. So, but it is true that you can get by with a small dish. Most of the heavy lifting in the interferometry would be done by ALMA. So you could, a 2 or 3 meter telescope could work. I just want to say it's not just a matter of sticking a heterodyne receiver on one of these probes and you have a node in the EHD. It's much more complicated than that.
Okay, any last question or? Okay, let's thank us on again. Yeah, I think so. So our last speaker is Dave Leibowitz, who will tell us about spirits. Thank you. Thank you.
Sorry, give me a second.
No worries.
It's a touch slow. I think your presentation is big. Okay, there we go.
It is.
Yeah, that's making it lag a little bit. You're good.
Thank you, Jake. Hi, everyone. It's a great pleasure to be here. It's a great pleasure to be able to take my mask off. Thanks to the organizers for inviting me to give this presentation along with my colleagues presenting other probe concepts. I'm going to tell you about one that's quite different from the others. It's an interferometer called SPIRIT, currently called SPIRIT. We'll rename it at some point. That stands for the Space Infrared Interferometric Telescope. I'm very proud of the science team that we've thus far assembled, and we'll grow a little bit more as we move along. Just yesterday morning, before I came to the workshop, I gave a presentation to a group called the Road to Mission Success at Goddard on a case study based on the WISE mission. It's near and dear to some of our hearts here, I think maybe many of us. So there are, WISE is a tremendous success. There were a number of lessons learned from that success. And there were 8 lessons in particular in my case study, and they can all be summarized by saying it's all about the people. So having a good team, as I've heard my colleagues express about their particular concepts, this is my team. I'm very happy about them. And we're working like gangbusters on this concept now, refreshing an idea that was last studied in 2004, as you'll hear as we go along. So we have 4 working groups, one on galaxy formation and evolution, another on protoplanetary disks and planet formation, another on debris disks and their structure and planetary system architecture, and finally, a group working on system modeling and simulation. I want to point out that Irene Chevai is somewhere out here in the audience, and she is our lead for the extragalactic working group. So you might want to talk with her about our concept as well. So here's a quick outline of what I plan to tell you about. First of all, what is SPIRIT? It has a foundation in community documents, so I'll point that out. I will give you a current snapshot of the science traceability, but it's a work in progress now that we've reassembled a science working group, and we'll be fleshing out those details as we go along, but I'll give you at least a snapshot of what it looks like at present. And then finally, how does SPIRIT work? So what is SPIRIT? SPIRIT is a probe class far infrared spatiospectral interferometer. That's a little bit of a mouthful. Spatiospectral means that it delivers data cubes, basically. So high spatial resolution, high angular resolution, but at the same time, spectroscopic information. So every field we study gives you a data cube, spatial spectral data cube. The wavelength range of SPIRIT is nominally from 25 to 400 microns. The angular resolution this mission would provide is about 1/3 of an arc second at 100 microns. It enables dense UV plane coverage for high quality images, but you can tailor the UV plane coverage to the observation that you're making. So you don't always need to fill the UV plane, depends on what you're observing and what you're trying to accomplish. As I suggested, it provides the equivalent of integral field spectroscopy, and it does that over roughly an arc-minute field of view. It provides spectral resolving power of the order of 3,000 or a little bit greater. It gets up to about 7,000 or so. It's wavelengths dependent, as you'll see. The sensitivity in a deep exposure would be about 10 microjanskis continuum, or about 10 to the minus 19 watts per meter squared on spectral lines. And as you've seen in other talks during the workshop, those are the kinds of numbers we need to reach to do the measurements we'll be talking about. It has a single science instrument, which of course buys down the cost, but that accomplishes all the science. It's a Michelson beam combiner. It doesn't have the kinds of challenges that Gary was alluding to with interferometry for EHT. Instead, we're not doing heterodyne interferometry, but direct beam combination. So you don't need a very high precision clock or any of those other kinds of things that would drive technology needs. This is based on technology that's available today, and we could develop and fly this, I say here about twiddle 2030, but now 2032 sounds a little more comfortable. So let's go with that. So how does SPIRIT enable science? It's designed to study how galaxies formed and evolved, how planetary systems developed, and how planets and planets like Earth acquire their oceans and life-enabling water. SPIRIT will apply interferometry for the first time in space, spatial interferometry, to achieve unprecedented resolution, angular resolution, matching that of JWST, but at 10 times longer wavelengths. SPIRIT provides a moderate resolution spectrum in every spatial resolution element. And with cryo-cooled telescopes, even though they're not very big, Spitzer was not very big, but with a cryo-cooled telescope and state-of-the-art detectors, SPIRIT would offer sensitivity about 10 times that of Herschel. So let's talk about traceability to community documents, starting with the decadal survey. I guess I don't have to repeat this because we've heard this multiple times already during the workshop, but we've heard the decadal survey very nicely positions the far infrared and tells us pretty much what should guide our thinking in terms of science goals. And they're all central to the broader scientific themes of the decadal survey. And indeed, these were the design drivers for SPIRIT when it was originally studied in 2004. There's a little web address there. You probably can't capture that QR code because of the thing in the way, but don't worry, I can point this out to you later on if you need to access our website with some old mission papers. You might wonder, we studied this in 2004. Why didn't we, do a new study leading up to the latest decadal survey? Well, the answer to that is that, as you heard Jason say, what headquarters was offering, NASA headquarters was offering in the way of a probe study at that time was, not a great deal of money. And we had already conducted a very thorough study. There was really no point in trying to conduct a mini study again, which couldn't go to nearly the depth we went to in 2004. There's a second community document that is very important to point out here, and that is the NASA Astrophysics Roadmap, Enduring Quests, Daring Visions, which talked about a mission called the Far Infrared Surveyor. And the Far Infrared Surveyor was described as follows. It's a mission that will pioneer space interferometry to resolve protoplanetary disks. It will directly measure water emission lines from young stellar systems identified by ALMA and JWST and detect the distribution and flow of water. It will provide critical information on the chemical and dynamical evolution of galaxies in the early universe. These are all themes that are, echoed in the decadal survey and about which we've heard a great deal during this workshop. And in terms of technical capability, the Far Infrared Surveyor was described in the roadmap as a mission that, when you compare it to Herschel, it would be cooled to 4 Kelvin to provide much greater sensitivity. It would enable multi-object spectroscopy, and it would have angular resolution sufficient to overcome extragalactic confusion. And there's another nice quote in the roadmap that I'd like to bring to your attention, and that is a multi-aperture interferometer will be required to achieve detailed sub-arc-second far infrared images of star-forming regions and galaxies. And this actually describes SPIRIT. So we have an opportunity now, for the first time ever, to make the far infrared probe essentially the far infrared surveyor as it was envisioned in the astrophysics roadmap. SPIRIT leverages a thorough mission concept study and available technology. And now we have a new science team that will help to refine the design concept. We can make small excursions around our baseline concept. But during 2004, when we studied this very thoroughly, we looked at 3 different point designs, each one in great depth and thoroughly analyzed. And they were deliberately chosen to be one very ambitious, one very unambitious, and then interpolated to look for the maximum science return within a probe class cost cap. Even then, in 2004, we were talking about probes. They just didn't happen when the 2010 decadal survey came along. Now, finally, we have that opportunity. But nevertheless, that's the essence of how the study was conducted at that time. So we chose that third in-between point as our current baseline mission concept. We can make small excursions around that without greatly perturbing the cost and staying in the cost box in order to maximize science as we now understand science needs. So SPIRIT provides sub-arc-second resolution for the first time in the far infrared. Here you can see the SPIRIT resolution as a function of wavelength compared with that of JWST and ALMA and other past and present far infrared facilities. For the very first time in the far infrared, it would bring the angular resolution way, way, way down into a very nice regime in which you can resolve individual circumstellar disks and measure the emissions of individual galaxies. Spirit will also offer, whoops, sorry about the way that worked out there. Wasn't that way on my Mac, but no worries. It offers sensitivity about an order of magnitude better than that of Herschel in a comparable amount of integration time. But as many of you realize, you don't necessarily make a 1 hour observation with Spirit because typically you're going to take advantage of the interferometer to measure higher angular resolution by moving telescopes around, changing baseline lengths and things like that. So in fact, the actual achieved sensitivity is greater than that one that's shown here, but it wouldn't be an apples to apples comparison if I showed it that way. So apples to apples, it's an order of magnitude better than Herschel. And then finally, as I mentioned earlier, it provides a spectrum in every resolution element. And here you can see in 4 spectral band passes ranging from 25 to 400 microns that the spectral resolving power ranges from about 3,000 to 4,000 with some wavelength dependence, as you see. And it's very comparable to the kinds of spectral resolving power in instruments like JWST MIRI, Spitzer IRS, Herschel PAX. These are workhorse instruments, Herschel Spire as well, that the community has used to achieve amazing science results, and we would certainly hope to do that with Spirit. So here's a look at what you could think of as the current snapshot view of the science traceability from goals in the decadal survey to objectives and then into measurement requirements. All of this is to be refined in the coming months. So let me just, without going into details right here, because I'm going to get to that in the coming slides, let me just bring your attention to 3 critical factors that drive the need for high angular resolution. In the Galaxies case, it's very important to be able to disambiguate the continuum in the galaxies that underlies the spectral lines whose line strengths you'd like to be able to measure, whose line ratios inform you about what those galaxies are doing. For protoplanetary disks, you want to be able to directly measure the distribution of things like water and HD. And so you can do that using the heterodyne high resolution approach and resolving the spectral lines and using Doppler tomography, and there's a little bit of model dependence to doing that, but if you can actually image these systems and resolve the spatial distribution of the lines, that's a very important alternative approach to getting to that information. And then finally, we can image hundreds of debris disks and use the debris disk structure to inform our knowledge about how developed planetary systems work and what planetary system architectures look like in a wide variety of cases. So all 3 of those things require sub-arcsecond angular resolution. That's really the point here. And now let's probe a little bit deeper into each of the 3 science areas. So first, the extragalactic case, where tentatively I'm calling the objective, as stated here, from far infrared spectra of tens of thousands of galaxies, learn how star formation, AGN mergers, and feedback affected galaxies since some high redshift, 5, 6, whatever. We can kind of stretch that a little bit. That requires wavelength coverage from about 30 to 400 microns, spectral resolving power of the order of 3,000, spectral line sensitivity about 10 to the minus 19 watts per meter squared. And most importantly, you want to be able to disambiguate the continuum. And rather than having multiple galaxies per beam, you really want multiple beams per galaxy to do that. The lines are important. I mean, this can't be overstated, and you've heard a whole bunch on that through very nice science presentations during the workshop. So I don't really need to say a whole lot more about it, but it's really, the information is in the spectral lines, suffice it to say. To achieve the decadal goal for a far infrared probe, we need to measure the far infrared diagnostic spectral lines in a large sample of galaxies over a wide redshift range. Spirit covers the spectral range shown in these couple of graphs here for the sake of illustration, and enables detection of these spectral lines. To measure the line intensity, one must know the continuum that underlies the lines. So let's probe this a little bit deeper. And here, a very familiar image from Herschel, the Herschel Deep Field observation of the Goods North Field. And you can see that, there's a lot of confusion here. Confusion is worse if the telescope is smaller than Herschel, which was 3.5 meters before JWST, the largest space telescope ever. If you zoom in on that and place a little piece of the simulated JWST deep field down in there, you can begin to get the sense of what you might be missing if you didn't have high angular resolution. So let's zoom in further. Here you see at the wavelength of 250 microns what the Herschel beam looked like. You can see that there are a whole bunch of galaxies in that resolution element. And to disambiguate the continuum, you need many beams per galaxy rather than the reverse. So if you compare that with what Spirit will do at that same wavelength of 250 microns, you can see a tiny little circle there that corresponds to the Spirit beam size at that wavelength. This is showing you a 1 arc minute by 1 arc minute sized field of view, JWST simulated field. And Spirit would observe a field like that, perhaps even 4 times larger than this, maybe 2 by 2 arc minutes instead, depending on whether we Nyquist sample with our detector arrays or not. So Spirit measures the spectra of individual galaxies in that area, and for every one of those galaxies, you would see a spectrum that would be something like this. So Spirit measures the dominant interstellar gas cooling lines and the diagnostic lines in the spectra of individual high redshift galaxies, and it covers the entire field of view at once at all wavelengths. So let's move on to the protoplanetary disks case. Here we stated tentatively as the objective to directly measure the distribution of water, both ice and gas in hundreds of protoplanetary systems, to learn how Earth-like planets form. And the wavelength range doesn't have to go as far out into the far infrared. You can be very happy to have 25 to 200 microns rather than up to 400 microns to do this. The spectral resolving power you would need for the ice about 30 or so, but for the water vapor lines, you'd want at least 3,000 or so, which we get. Here, you're going to resolve the objects, so you do need pretty extraordinary sensitivity. We have to study this further, but we estimate that on a per beam basis, about 10 to the minus 20 watts per meter squared, or about 10 milligauss per beam on the ice sensitivity, which is certainly well within our range, and about 1/10 of an arc-second angular resolution. We know an awful lot about these protoplanetary disks from models and theories and ALMA observations, and soon JWST, but there's still a lot that's unknown and that we need the far infrared to measure for us. Water, we hear that all the time. Water affects planet formation. It's essential to planet habitability. It's not observable from the ground. It is present in protoplanetary disks, both as water vapor and as ice. In fact, we think a good deal of the water is frozen out onto dust grains. And that ice affects the grain stickiness and helps planetesimals grow. All theoretical notions and, well, maybe some lab-based measurements as well. But it sure would be nice to have some better empirical observations of these objects in the water ice bands as well as the water vapor lines. To learn how Earth-like planets form, we need to know the spatial distribution of water vapor and ice in protoplanetary disks in a variety of evolutionary states. So you need a statistical sample of these objects captured at different states of their development. So what are the next steps? The water vapor distribution can be retrieved either by using Doppler tomography and high resolution spectroscopy, which is the Chris Walker's OASIS MidX mission proposal would do. So that's a pending proposal, as Chris mentioned. An alternative to that is to directly image the disks and map out the water distribution and the ice as well. And in fact, you can't do the ice through heterodyne high resolution spectroscopy. These are broadband features, as you know. Note here, as you've seen in many previous presentations, the rich water vapor spectrum and the ice features pointed out there. So next steps continued. If you could resolve one of these disks, here we show an example of the kind of spirit resolution at about 100 microns in a grid overlaid with the TW Hydra disk as an example of the kind of mapping that you could do if you had an observatory like Spirit. And in addition to the water, you've also heard about the importance of the HD 112 micron line. There's also the 56 micron line. Those lines are very important as they inform us about the total gas mass in these disks, as you've heard. So let's move to the final of the three main science drivers for the mission as currently envisioned, and that is debris disks. The objective here would be to image hundreds of debris disks to find planets in orbits like those seen in the solar system and measure their masses, where they are, how massive these planets are. And it's an analog to seeing the structure in Saturn's rings formed by gravitational interactions of the particles with orbiting moons. You use that same technique. The requirements in terms of measurement requirements, you need the short wavelength end of Spirit's coverage from 25 to say 100 microns. You don't need very high spectral resolving power, of the order of 10 would be fine. You really want something like a spectral energy distribution in each spatial resolution element. You would need about 1 millijansky per square arcsecond surface brightness sensitivity, and you'd like about 1/10 of an arcsecond of angular resolution. So if you could do that, as I was alluding to, you would have a new technique for measuring, for locating and measuring the masses of planets, filling in a part of the planet architecture domain that is not well probed through any other method. That's using the debris disk structure. So people who work in this field talk about the Fab4 debris disks, Fomalhaut being one of them. And those became the Fab4 when IRAS and Spitzer and Herschel observed them. They can be well resolved by these past missions. But if you want to see a much larger collection of these objects than 4, you need to be able to do this kind of a measurement out to 100 parsecs or so. So that is what we're trying to achieve here. So here's a picture of the Fomalhaut disk as imaged by Herschel. I think this might have been about a 70 micron image. You can see that there's a planet candidate there. That's the kind of thing you might infer from this structure. If you take Fomalhaut out to 100 parsecs, it gets to be pretty small. And there it is compared with the Herschel beam size at 70 microns. So you couldn't do that if Fomalhaut had been at 100 parsecs and you had only Herschel. But if you want to measure hundreds of them, you have to be able to resolve things like that. And that's what Spirit would do. So again, at 100 parsecs, here's the Spirit beam size at 70 microns next to what Fomalhaut would look like at a distance of 100 parsecs. And you can see that it would be a well-resolved disk structure. So you could capture hundreds of these objects with Spirit and measure their structure. Okay, so how does Spirit work? This is shifting gears now a little bit. And in a nutshell, on one single slide, I would say that, the easiest way to think of Spirit, it's sometimes called double Fourier interferometry. It does both spatial and spectral interferometry. The spectroscopy comes from a Fourier transform spectrogram. So it's got a moving optical delay line in the beam combiner, but it's combining the light from two separate telescopes. And in that sense, it's an imaging interferometer as well. And as a result, as I mentioned, you get a spatial spectral data cube. We have a kind of detailed breakaway view here. Spirit would rotate as it makes its observations. The telescopes can move back and forth along a structure, or perhaps they would be fixed along, on telescoping booms that would retract and re-expand. We're going to be looking at that trade, but the early concept back in 2004, there were no such thing as retractable telescoping booms. So that's a new technology we want to take advantage of. At the time we studied it, we had these telescopes moving on trolleys along a truss structure. Either way, we would like to be able to measure many different baseline lengths and many different baseline orientations to essentially be able to densely fill the UV plane and get high quality images. There's the single science instrument that you can see in the center there. That's a Michelson beam combiner that takes the light in collimated beams from each of the two telescopes. These are 1 meter diameter telescopes, I should say, and they are cryo-cooled to about 4 Kelvin. The maximum baseline length that gives you that third of an arc-second resolution at 100 microns is about 36 meters. There are all sorts of other details here that I probably don't have time to go into. So in summary, Spirit was designed to address the decadal survey science goals, even though it was studied way, way, way before the latest decadal survey for a far infrared probe. The far IR probe could be the far infrared surveyor as envisaged in the NASA astrophysics roadmap. Spirit's measurement capabilities are an excellent complement to those of JWST and ALMA. The Spirit concept is anchored to a thorough design study with 3 distinct point designs, each thoroughly studied, and the technology is ready to propose this mission now. I hope we do, and thank you very much.
Any questions for me? No. We can run a mic over there. So.
Your mic. Your mic. You have to run it.
Let's say you got 1,800 days in the mission. You mentioned 3 disks and thousands of galaxies. What does an observing program look like? How many objects do you image fully, and how long does that take? How much do you expect? Just give us an idea of what the mission profile looks like.
Yeah, so we'll have a much better answer to that question, Charles, once we, study it. We're actually going to be developing a design reference mission for it. The observations themselves, I should have mentioned, will be largely geo-driven by the community. But as I picture the design reference mission in my head, for observations of things like debris disks or protoplanetary disks, you would probably, certainly for the debris disks, you would want fairly dense UV plane coverage. And to do that, it takes about 1 day per observation. So the 1 day gives you essentially complete UV plane coverage and extraordinary sensitivity. And 1 day of science integration time actually takes 29 hours of wall clock time. So on average, you could think of an observation like that being a day. And if you want to do 100 of those objects, there's 100 days. The extragalactic observations, you would probably pick a handful of well-studied deep fields and measure their complements in the far infrared. And a typical deep exposure like that with Spirit would last probably about 2 weeks to build up the signal strength and get all that angular resolution. In that case, you probably wouldn't need to do very dense UV plane coverage because you're not trying to image those galaxies, you're really just trying to pick them apart. So you might just pick a couple of long baseline lengths and rotate the interferometer to see the modulating signal from each galaxy in the interferograms. So figure, a couple of weeks per deep field. So again, maybe that's, a couple more months or so of mission lifetime on extragalactic work like that, giving you a very large sample of galaxy spectra. And then protoplanetary disks, you would really want to tailor the UV plane coverage, I think, to the individual object, its known size from other measurements and its distance and that kind of thing. You wouldn't probably resolve a lot of them with, the same way you would want to image the debris disks. And that's, subject to study, but you could, figure again about a day per target. So maybe another 100 or so days of observation per target like that. And then, of course, there's lots of leftover mission lifetime that you would spend on many other things.
We're pretty much at time. Maybe we'll get you into the session.
Thank you very much. It's exciting to get to some parts and resolution in a time. Wonderful. So I had, so you're also measuring phases of these fringes in some fashion, right? By modulating the paths in some way?
Did I hear you say phases?
Yeah.
Yeah.
phases of fringes.
Yeah, you're measuring interferograms.
I can talk to you about that later, but I had another question. Is there a non-interferometric mode in which this instrument could operate? Because your field of view is limited by the spectral resolution, right? Effectively.
Yeah.
And maybe you can accommodate other science cases if you had a non-interferometric mode.
Thank you for that question. So yes, there, even in the current design, you could think of this as having a non-interferometric mode in the sense that in the 4 broad wavelength bands, you get a flux measurement as the DC pedestal on which the interferogram sits. So you have 4 flux measurements as, at the diffraction limit of a 1 meter diameter telescope, cryo-cooled, so still extraordinary sensitivity. You could modify the design a little bit relative to our current baseline, and it's well worth considering doing so to operate as a kind of conventional FTS behind a single aperture telescope. And then you would have an R of 3,000 to 7,000 kind of spectrum, not just the broadband for measurements, but a spectrum across that entire 25 to 400 micron wavelength range. So that's it's well worth considering doing that, but it's not part of the current design.
All right, let's thank Dave again. Okay, we're going to roll. Sorry. Doing 2 things at once never works that well. That's a fine thing to leave on. We're going to roll into an open session here. I don't know that we thought through the goals exactly, except we wanted an opportunity for all of us to sort of start asking questions, perhaps of the PIs or representatives of the science teams. Dominic's in the corner of the room. I think that something that's new we didn't know yesterday is that the parameters have changed a little bit. And moreover, the draft AO is a draft. And if we as a community want things included or changed, that is a possibility. So if you're seriously thinking about these things, proposing them and on the science teams and whatnot, and there's a space that you would like to explore to change the AO, we could have that discussion. The other part of this, I guess, is we have 5 questions for you guys after lunch, like we did yesterday. Those 5 questions are all probe related. I would invite you to go look at them if you haven't. If there are pieces of information you need to know about these concepts to have a coherent vision of what your answer might be, now would be a good time to ask. And I guess just the final thing before I quiet down is Gary reminded me of the famous romantic film Top Gun. Earlier today, I'm paraphrasing here, but we may be in competition, but we're all on the same team. So let's try to keep everything positive and constructive. Okay. Oh, I guess I wanted to say, we've heard a lot from the people with gray hair here. Perhaps we should start by having a question or a thought or something from somebody who does not currently have a permanent position. Anybody feel like speaking up? Going once, going twice? Okay, Meredith says there's a good Zoom question.
Yeah, so we have a question in the Slack, which is for all of the proteins that says the time domain is an important dimension of mid through far infrared science and was called out by the Kale survey for all of astronomy. Do you anticipate that your design will allow for agile observing short integrations of many sources and provide a stable platform for precise, say 1% relative calibration across time? I'll just throw that out to the broader community.
Can you hear me? Okay, so this is Jason Glenn speaking for Fremont. So we've been thinking about transients lately, and we do think that this is going to be important, and we're starting to assemble requirements for the observatory to enable us to do follow-up. The relative precision of 1% on calibration could be achievable. Absolute calibration is going to be more difficult. If there's specific requirements that you need, please contact us and or submit a science case to our survey so we make sure that we can incorporate them at this time rather than later when it gets more difficult and probably more expensive.
So this is Dave Ligo speaking for Spirit, and I would not describe Spirit as a particularly agile observatory. I think you can look at the picture and almost infer that. But on the other hand, you know, here and I'm thinking in real time. You know, one observation that might be interesting to measure is transients in debris disks, where every now and then a couple of objects bump together and smash up and make some dust. And Kate Sue on our science team recently had a very nice Spitzer result published in which she saw that kind of measurement being in the time domain. We could certainly, you know, revisit the debris disk and do a kind of before and during and after measurement if we knew when the transient event would occur. And I think maybe that would be the challenge for us is having some independent knowledge that would say, look now. Apart from that, you have to get lucky, and I don't think you want to do too many revisits with Spirit with maybe full UV flame coverage in order to get lucky. But if you knew when to look, you would be able to not only see that kind of structure appear, but you would know where it's happening, which might be quite interesting.
Hi, this is Chris Walker for Saltus. So one of the nice things about Saltus is it has a very large aperture, so it has very high sensitivity. So we can integrate and get the results very quickly within a few hours for a particular object. The other thing it has going for it, it's a large aperture, so we have a very small diffraction beam up at the wavelength ranges, which is diffraction limited, and even on the shorter wavelengths, the scale is pretty awesome. So for instance, it'll be about a quarter, 0.3 arc seconds at the fraction of the beam to a few arc seconds. So that makes it very agile approach for time-dependent phenomena.
Yeah, this is Ali Mandel and Master Goddard. I'll talk later in the presentation about how we can integrate a self-calibration scheme into a sort of simultaneous infrared coverage for mission, any of these missions that will help to calibrate over time down to the levels that might be needed for transients. And so I think there's ways that we could mitigate that absolute calibration problem.
I'll interject here, and I ask everybody to bear with me today because I am clearly the unbiased side, which is IR STIG co-chair with Mike, and then have bias side, which you'll see as I give my talk this afternoon, but is absolutely something we've been talking about for first. And a lot of my science work is in stellar activity and flaring and transient phenomena. And I will then toss it out as sort of a broader discussion to say that the far infrared community has largely not actually been very involved in time domain and transient science. And I think that's through some community and strategic choices in how we design our missions. And clearly there's a lot of interesting science to be done there. So if we as a far infrared community want to actually attract other astronomers who maybe are not in this crowd, right, who aren't convinced that this is the right wavelength, we should put some careful thought into that in order to how we actually enable this sort of time domain transient science, because it's not easy, and even telescopes that do this well aren't actually perfectly enabled for it. So there's some careful thought that needs to be done there.
Probably if this was mentioned in regards to time domain astronomy while I was out in the room, but in the decade ahead, before these probes fly, the LISA mission will fly. And a lot was made in the decadal report of multi-messenger astronomy. I don't know the answer to it, but it might be incumbent on our community to do modeling of whether there's a prayer of seeing an infrared signature of black hole coalescence. These missions will have the benefit of some advance notice from LISA of these coalescent events. But I don't know whether the expectation is for infrared, a strong infrared signature, and what the flux sensitivity would be required to detect it. But I think it's worth investigating.
Jerry, if I could jump in, Lisa will get data down.
Microphones. Nobody on Zoom can hear.
Oh, 2037. 2037, just correcting it.
Oh, okay.
Let me say it into the microphone. People on Zoom.
Oh, sorry. Yeah, okay, sorry.
It's launching.
Lisa data will come down in 2037.
Okay,
Launch is
well,
2035, 18 months before they get data down.
now it's at launch.
ESA's new schedule? Yeah. Launch in 2037, data in 2039. Okay.
So for people on Zoom, that's saying that LISA will launch in 2037, so we can expect to have data from it till 2039. So that's relevant for the timeline.
Okay, well, not to be overly pessimistic, but even probes slip. But it would still be interesting to know whether just theoretically we have something to contribute to this multi-messenger feed.
One question concerning several of the probe concepts about sun fields. They probably want to look away from the sun, oriented away from the sun in some sense. Does that mean that the sky access at a given time is always rather limited to a rather small probe?
Thank you. This is Dave Lyndwood speaking for Spirit, and I didn't show it at any given point in time. Well, first let me answer. Over the course of the mission lifetime, Spirit, as currently designed, would be able to have a viewing zone that's plus or minus 20 degrees around the ecliptic plane. And you get that entire band as over time as with the Earth orbit around the sun. At any given instantaneous point in time, you have a viewing zone of the order of 40 by 40 degrees within which you could look. And then that just moves around the sky. So there are some limits, and those come into play more for something like Spirit with its architecture than they might for some of the single aperture telescope concepts, where you can passively shield the larger portion of the telescope. So that was a compromise we made in our mission architecture.
Thank you. So this is Jason Glenn again. So following up on what Dave said, the field of regard for the single aperture prima is going to be larger than for an interferometer, but you still can't point near the sun. However, with the sun-Earth L2 orbit, that means if you have patience, you can get all of the sky over a year.
I just wanted to make a couple of general points. I encourage all the probe mission concepts to leverage other facilities that would come into picture on the same time scale. Not just because I'm from Nation Radio Astronomy Observatory, but NGVLA is going to be a leading facility during this time. And in a broad sense, one can say that, of course, we use every other facility that is there, but it would be good to have concrete ideas on how the specific capabilities of the NGVLA, for example, I'm just giving an example, would synergize with your probe. And in fact, participate in the NGVLA science projects. I mean, it's in a stage where we are hopefully getting into design and development phase. This is the time where you should come and tell us that for our infrared projects, this is how NGVLA can play a role in this. And that would be wonderful. And we can leverage NSF and NASA funding to bring things together. That's one point I wanted to make. And the other is about the long wavelength end of the far infrared. I mean, you know, I've been trying to say every now and then in this meeting about the possibility of observing the photon rings around the black hole in 87. This is the topic that's of great interest to humanity, I would say, in terms of how much attraction it became when the first images were made. Gary, of course, made the point that it is not as simple as just putting a heterodyne receiver, but the clock and the reference systems are improving by the day, and by the time these missions fly, they will be in a very viable state, optical clocks. And with respect to data transmission, NASA's deep-space optical communication roadmap pretty much allows for large amounts of data to be transmitted. So these are possibilities that exist, and I would encourage all the missions to actually consider this to see if it can be replicated and be. Thank you.
I have actually a question for Dominic or sort of program folks. This is we saw from Dominic, and we've all seen in the AO draft AO the very specific writing of the science priorities of the FAR IR probe. But then over the meeting here, we've seen science discussions drift out of this narrow write-up. For example, time domain astronomy was not listed at all in the FAR IR probe. That was listed in the CAO, but not for the probe. And of course, exoplanets characterization came up several times, will come up again. So my question to Dominic and frankly to the headquarters is, with the narrow writing in the draft AO, how will you sort of evaluate, or how will these things be considered in evaluating?
Well, I'll do the best I can to try to address that question. The decadal survey seemed to indicate, this is my reading of it, I don't have an official policy, that there are certain things in a menu list that you must be choosing from. But there's nothing that I could see that said you can't do other things as well. There's some key word in there includes the following things, but it doesn't say must be among the following things. That's my interpretation of it. And so we would follow the kind of process that we normally use in peer review, although mid-X and specs don't have this caveat, that there must be some of the elements of things that the decadal survey has specifically called out from FAR. But additional science that aligns well with the decadal survey, for instance, time domain and multiple spectroscopy, which wasn't necessarily explicitly called out, but is clearly of strategic interest, is part of what gets factored into the overall science benefit in the science review panel. We have a panel specific to that for all specs So yes, I think you can get bonus points for those other things, as long as that's not the only thing that you're doing. We ignore the things that you'll sort of said that we should be doing. Is that a sufficient answer?
Kimberly, a question for the probes and also just the community. The classic piece. It has to do with this interesting opportunity that the probe line provides within the planetary community. It's large enough money to allow potentially either a large aperture or a cryogenically cooled medium-sized aperture, depending on height and size. But it's PI-led. And usually a PI-led mission doesn't necessarily have a large general observatory concept to it. And the first team mentioned that their design is 90% Geo. So I was kind of curious about how the other probes are kind of looking at the Geo versus GTO ratio. And also the fact that the foreign community has been accustomed to consortium-based observatories, Spectre and Herschel, where you had instruments that had PIs, but then it was always for the community. So the question, sort of is, what's kind of the thinking of the Geo to GTO time? And also, if you did have a nice split, how could a Geo program be done? Is it throughout the mission, or is it always tied on to the end when a GTO has been completed?
Before we hear from the particular concepts, I did want to mention that this is a question this afternoon for one of the groups is exactly flowing in the direction, which is, as a community, what would we like to see? And the answer could be 0, or it could be 100%, or something in between, and there's different drivers. I know people will be confused on this sort of thing, but this is very much an open question.
Anybody want to tackle it?
So, can you hear me? This is Jason Webb speaking for Prima again. Our reading of the community announcement is what we base our current thinking on, and we're very eager to see the draft AO when it comes out so that we can refine, develop our strategy. But our reading of it is that the Geo program, NASA is holding a lot of funding for that. We're looking at a lifetime of probably 5 years, where the guaranteed time science covers something like 1 year, and then there's several years of open time. We haven't thought at all about how that would be structured. And in fact, the lifetime of the observatory could far exceed 5 years. You shouldn't take what I'm saying now as our plan, because we don't have enough information yet to develop one. We'll know more after the draft AO comes out. And I think there were more compliments to your question, which I forgot, and I apologize for that.
Oh, it's sort of whether, yeah. He asked many questions in one question. But it was just sort of like, the probe is a wonderful opportunity because it's a paradigm shifting approach to the next generation of doing this type of observatory. And it comes with, we're doing it differently. And the old model was a consortium based where we had instrument PIs, and then each of the PIs said, you have that, but then you had a general observatory. Then you have other paradigms where everything was a general observatory, like Sophia. So this is sort of a mixture. And so the question is that, should the probes, it was sort of like, is the probe model steering away from instrument PIs and consortium approach, or the PI-led component is a good way to explore, because we haven't done this yet for this community. PI-led missions of this large class are done frequently in planetary astronomy, but planetary astronomy is quite focused. Astrophysics is more general, and this is a discovery space. So, I mean, just sort of along that lines of an opinion of, is this something that's very something to be behind, get behind?
Okay, so I'll take a quick stab at this and then I'll pass it on. And really, I think in my mind, you answered the question when you asked it. This is new to astrophysics and we're finding our way through it. We don't have an answer yet to the question about instrument PIs, for example. And there's not likely, at least in our case, to be a lot of instruments. Okay, so I don't know. I think that we'll know more when we get the draft AO. There may be other people in the room who can maybe have more information.
This is Dave speaking from Spirit. My answer is almost the same as Jason's, in the sense that in answer to Charles's question earlier, I outlined, how much time we would spend doing the various observations I described. And if you add all of those up, they take about a year. And those, I wouldn't, describe them as something that's, a proprietary data period. It's more about establishing a legacy database for the community to use in coming years thereafter. But that's still, as Jason was pointing out for Prima, for Spirit, again, that data set would take about a year to accumulate, but out of roughly 5+ year vision. And so there's plenty of time for the community to go off and have wild thoughts and discover things that we can't even imagine today with that general observing time. So that's all baked in. In terms of instrument PI kind of thing, as I mentioned, Spirit has only a single instrument, and in fact, it's a little bit easy to kind of envision the entire thing with its 2 telescopes and beam combiner as the instrument. So it really would not be natural to have, a competition for an instrument building PI. It's really part of, what's baked into the overall plan for the observatory. So we wouldn't do that kind of thing with an external PI. It would just be part of the team's development. And it really all needs to be systems engineered together.
I just insert something maybe somewhat provocative here and also remind everybody, right, the time scales for these things. We would launch this in like the mid-2030s. So I feel like it's important to keep in mind that all of us in this room who are making these decisions now are not actually going to, we're going to be way longer in our careers. The people that are the grad students and the undergrads right now are the ones that are actually going to be the new faculty members at the time that this launches, right? So in my mind, it's incredibly misguided to think of it in any other way, because we should be enabling those early career scientists who aren't even in the discussions now to actually get to do something cool and creative. Just throw that out.
So hi, this is Chris Walker for the Soltis team. The way we view it is we're providing a new observatory for the community. And in designing that observatory, we have to come up with some baseline science, the obvious science, a lot of which I mentioned some of it's obvious things to do with a new observatory in space and the far infrared. But beyond that, it needs to be open to the community. The other thing is, in case of Soltis, at least 50%, 70% of the time we go to the community. And then another thing is that none of the data would be embargoed. So as soon as the data is taken, calibrated, and worthy, we would post it. And everyone can publish it. At least that's my personal.
I have a question concerning those missions that are already operating or operating. There already are, there's a quick question, to what extent do you have larger key projects that consume a lot of time and support a larger team compared to small projects by individual observers? That relates a bit to the question, to what extent do you want to have geo-driven proposals on probes? I was just wondering, from the existing observatories, are there specific opinions about what does it mean when an observatory has
does or does not have projects that are driven by smaller teams of observers? What does it mean for the science that gets delivered for the education of the next generation of scientists? Do we in particular have something from Sophia? You must have thought about that.
Yes, we certainly did, and but I'm speaking here my personal opinion, but the being an observatory, you serve the entire community, and so you try to do what your particular observatory can do best, but at the same time you need to spread the opportunities. You need room for the small projects. So small projects, a few hours or so for the small PI group or just one PI, whatever. But then you also have to make room for these larger programs. In Sophia, we call them legacy programs, and that has examples from prior missions like Redshift and Spitzer and so forth. Simply because you want to enable the archive research as well later on. So for that to be done efficiently, you need reasonably homogeneous data sets that can be analyzed in a statistically meaningful way. So it is much harder to kind of cobble together all these different, very differently taken data sets from individual PIs. So, you have to have a healthy balance between those. At the moment on Sophia, we have chosen a third of the time goes into legacy programs, 2/3 of the time goes into general programs. And it seems to work pretty well.
So probably other people know the answer to this, which is good. Well, I'll ask it. So is there for Sophia a system like there is for, say, Hubble, where observers apply for time and then there's funding associated with, if you're awarded, some amount of observing time, NASA provides funding to, pay for people to do the analysis. So is that the way it works with Sophia as well? And is that the plan for these probe missions?
Yeah, I'm not the right person to answer this. Is Margaret there? Otherwise, I can, of course. But...
Oh, right, yeah, so Sophia had an archival call just focused on the Sophia archive to bring attention to it last year. And we gave out $1.8 million for 11 proposals, and it's for things that were in the archive. And, a lot of the legacy programs were capped. I mean, there were other things that were capped. There's a lot of unpublished data in the archive, but the archival value is important for the longevity and the big impact.
Yeah, but I was more asking about this.
For Hubble, this is a mechanism that really motivates people to apply to submit observing proposals. I mean, I know every year groups that do this is like their main source of funding. So is there a similar mechanism for groups who apply to Sophia for observing that they get, if they're selected and they get a certain amount of time observing, that comes with funding for students and analysis?
Oh, yes. In fact, it's starting in cycle 9 or 10, I'm losing track. We put a minimum grant of $75,000 because we want the investigators to be able to hire and train students. And we were getting constant feedback from our Sophia users group that if you get a 2-hour program, you don't get with 20K, you don't have enough to hire a student. So, but we did an evaluation of that. We do think it's important to have people properly funded so they can support a student. And I think in cycle 9, and we did it retroactively, it was 40K. And then in for future in cycle 10, through another analysis, we raised it to 75K. But But yes, we do want to provide proper support for the observers and anyone who has a great science thing for the archive.
Okay, this is great conversation. I think we have opportunities later in the day to continue it, but it seems like everybody needs a break. So I'm going to invite Jake up here to talk about some logistical stuff, and then we'll go outside and take a photo, and then we will have lunch and reconvene at 1:30.
All right, so just a few logistical points. You all heard about the lunch options yesterday. For those who weren't here yesterday, there is lunch available in the building upstairs, I believe. Some people have found it. And then there are a number of options very nearby. We're just walking approximately this direction. And then there are further options if you want to walk about 15 minutes. But primarily what I wanted to talk about today was the social event we have planned for tonight. At 5 p.m. immediately following the work group discussion, there will be a bus outside, 56-person coach bus that will take some number of us who want to take the bus to Spirit Hound Distillery that is in Lyons, Colorado. It's about 20 minutes away, 25 minutes away. The remainder of us can break up and carpool with people who are willing to drive others. So we'll organize that as we're leaving. We'll be at Spirit Hound until 9 p.m., at which point we will, those on the bus will return, and those carpooling can organize individually. We just want to make sure that people don't get left in Lyons because it is quite a long walk back to Boulder. There will be a food truck on the location and other restaurants within walking distance. The address is there, but there's more information on the workshop website. So just in case you're driving, feel free to come up to me and I can help you get directions. But effectively, we're down here. This is sort of the main part of Boulder. Going to be driving north about 20 miles to Lyons. This is the mountains and the foothills, and you'll be mostly taking Route 36. And Route 36 will dead end into a highway, the Ute Highway. You'll take a left. You'll see this sign that says "Whiskey from Colorful Colorado," and that's where we're going to be having the social event. And there'll be tours of the distillery. We'll be breaking up into 3 or 4 groups, and people can go on tours, as well as have dinner, so we can organize more as we get there. I just wanted to share that information. And I think now we're going to go outside and take a photograph of everyone. Everyone is amenable. All right. We're going to start our next session of the day. And I'm here to welcome Matt Bradford from Project at the Propulsion Lab. We're talking about Fremont Internal Fire Improvements. Go ahead.
Okay, thanks, Jake. Okay, so I'm delighted to be here. Good afternoon. And so, yes, I'm here as a key member of the Prima team, but I think what I have to say will be of interest to all of the concepts and connecting the science to the implementation. So I can't resist, I'll try to resist talking about science, which will be hard, but I'll try. But I can't resist reminding us of the opportunity we have here in the far infrared with a cold telescope. And there are some numbers that we can use when you're in the elevator with your X-ray counterparts or whomever you want to convince. So this is a plot from Dominic Benford et al., some work that I was involved in along with some others at Goddard and JPL about 20 years ago or nearly, back before Dominic took the reins of power and influence at headquarters. And around the time that Webb was kind of getting going and we were thinking about cryogenic telescopes in space, it was a period of some collaboration. And here you see a nice figure that Dominic prepared showing the backgrounds for telescopes of various temperatures, and then the sky background here in the bottom. And so these are many orders of magnitude on this plot. And so you can see a warm telescope, and then the natural background. So this big hump here in the middle is the zodiacal dust. There's a little contribution from the Milky Way galactic dust here at about 100 microns and beyond. And then the microwave background comes up, of course, at the longest wavelength. So that's the fundamental limitations that we have. And it's about a factor of 1,000,000 in background. So that's about a factor of 1,000 in sensitivity for a given measurement, if you're background limited, and a factor of about 1,000,000 in speed, okay, for a given instrument approach. And that's not that different from in the optical waiting for the sun to go down at a good site without the moon. That's about somewhere around 30 million. Okay, so it's a little bit more, but you know, we can pick a site like the Boulder night sky that's probably close to parity. So this is a massive improvement, and I think we need to bring that forward as we make the case for a far-infrared probe. Okay, so I'm going to dig into the vision for the instrumentation we have for PRIMA, but I think again this is going to apply to FIRST, to SALTIST, and actually to SPIRIT as well. So the thing we're most keen on, I would say, with PRIMA is the spectroscopy, and so Asanta, named the telescope after spectroscopy for good reason. The imaging is somewhat in place. Here's a Herschel view at the long far-infrared wavelengths, and shows the beautiful structure in the far-infrared sky. This is the actual structure of the universe. The dark matter is 3.6 square degrees. Every pixel in here has information. Every pixel in here has a source. And so we are going to study these sources, measure their redshifts, learn what powers them, and we'll do that in a couple of different ways. First, of course, we want to be able to identify targets of interest, follow them up, and obtain a full wideband spectrum like what you see here. So Jason showed this, Asanta showed this. This is a nearby galaxy spectrum, and there's all sorts of fantastic diagnostics. And with a cryogenic telescope, we can obtain spectra of pretty much anything in this map that Herschel made in the continuum. So that's point number one. And of course, we'll be sensitive enough to do this for many hundreds of galaxies, if not thousands, over the course of a long mission life, including the Geo Program. Now, also though, we want this to be able to make blind surveys. If you want to make a plot like the Medal plot, where you're measuring an absolute quantity as a function of cosmic history, you have to do a blind survey. And so this just shows example fields that we would survey with the PRIMA spectrographs, mapping every pixel, every spatial position in these maps with good sensitivity. Of course, the sensitivity that you get in the map will depend on the depth, will depend on the area. The depth that you get will depend on the area. And so you can envision constructing wedding cake type surveys where you're trading depth and area to go both deep for the high redshift objects and wide to cover to overcome cosmic variance of low redshift. So these are just example fields. All of this is being optimized, but the instrumentation is designed to be able to do both this pointed spectroscopy and the mapping. So let's look a little bit at how this will work for PRIMA. And apologies for those of you that attended our Pasadena virtual workshop last week. Some of this is going to be the same, but if we just zoom in on a 1/4 degree section here of this Herschel map, now I'm going to look at what the slits of PRIMA look like. But first I'll point out here with a Spitzer MIPS 24 micron image to the same scale that with a 2 to 3 meter class telescope, we will be able to resolve most of the light near the peak of the cosmic far-infrared background. So yes, at the long wavelengths, there will be confusion, and that's certainly the point that Dave is making with SPIRIT. That's certainly true. However, it's not hopeless. If you consider, for example, a 2.5 meter telescope will have an image like this Spitzer 24 micron map with PRIMA, and that's near the peak. So you're going to resolve most of the light at the peak of the cosmic infrared background. That's a big step towards overcoming confusion, even before you start spectroscopy. Now, the slits for Prima, so the spectrometer is going to cover this full band between James Webb and what you can start doing with at least that's our vision, that's the goal, and that we divide into 5 bands. So this is the same approach that Safari on Spica had, that we had with the Origins OSS instrument. It's fairly straightforward. I think with Saltus, Chris is envisioning a similar kind of approach. This is what it will actually look like if you design and build an instrument. So what you see here are 5 diffraction limited slits. And so the width of the slit is basically 1 diffraction limited beam on the sky. And so at the short wavelengths, 25 to 40 microns are band 1. That thing's about 4 arc seconds wide, depending on the telescope diameter. It's going to have a length given by the size of the detector rays that we can field. And so we're going to most likely bias towards larger arrays and longer slits in units of f lambda at the short wavelengths for obvious reasons that you can see here. You want to be able to recover some of the mapping speed that the longer wavelengths have. You want to give some of that back to the shorter wavelengths. So we're going to optimize this, of course, but you get the idea. Now, I want to point out that it's very important if you want to talk about sensitivities toward point sources. You need to have a diffraction limited slit. So, for example, if the Saltus telescope ends up being a light bucket at the short wavelengths, you're not going to get the sensitivities that you calculate just from a single mode diffraction limited system. You're going to have to integrate a lot more background onto your detector. You have to capture a lot more background to measure the source. So these are important factors that need to be taken into account when you consider the actual practical sensitivities. So start at 25 microns, go all the way out. Now 25 microns is a placeholder. James Webb goes to 28, but of course we all know it's degrading quickly at the as you get out past about 20 microns, and some would argue even shorter because of the thermal background. So this is something we're looking at. But of course, we have to trade. We can't do everything. You can only cover efficiently something like a factor of from 1 to 1.6, 1.65 in a single module. And that's because of these reasons that I'm alluding to with the diffraction limited coupling and the background that you need if you make the slit too large. So there are some limitations, and we think we can muster 5 bands, but we'll see. So if we did, we'd reach out to 330 microns. Now here you see the slits separated on the sky. That's the simplest implementation, of course. We are also looking at aligning the slits, and this will allow you optimal single source follow-up capability. Because you can point the instrument, and then through the use of polarizing grids and approach, you can couple all slits at the same time. Again, larger field with the longer wavelength slits, no problem. But for given sources, you could couple all bands at the same time. And so that's what gives you this powerful general observer capability for following up any source of interest. A Redshift 10 galaxy discovered, let's say, in the millimeter with a dropout, we can go take a spectrum of that source. Right? Yeah, there's some, so there's some optimization. There'll be a penalty to do this alignment. You're going to lose some light because we're going to have to use a polarizing grid to do that. Okay, so yeah, this is along the lines of what everyone else is envisioning, simple all aluminum spectrometers. I think Chris showed us the Spitzer infrared spectrograph figure. This is very much in that vein. Resolving power of 200 is what we're baselining. Another thing that we can optimize. But that's a very nice figure. It's kind of an intermediate number between, say, the low-res Spitzer modules and the high-res Spitzer modules. And we know you can detect lines efficiently at that resolving power. These are low-res spectra, especially you see here on the lower right. So we'll have more resolving power than that. These, by the way, will be cooled. Well, at least the longer wavelength spectrometer modules need to be cooled to a Kelvin or thereabouts to prevent the background from inside the spectrograph module limiting the sensitivity. So that's another thing to keep in mind. Okay, so that brings us to our fact sheet, which I think is out in the community now. So I don't need to go through too much of this, except I'll highlight sort of the fundamental kind of observational capabilities of the drug. And so of course, point source sensitivity, as I was describing up here in the upper right, and you see 2 kind of bounding cases. our, what we call design value, and what we call our baseline, which is, I consider kind of a worst case. Now, these include telescope diameter. There's two values assumed here, 2 and 3 meters. Detector sensitivity, there's 2 values assumed here. And some other factors like the instrument efficiencies, all of which go from sort of a best case to a worst case. And I think I'll highlight even our design values are based on real life as-built instruments that we've used on the ground. So all these various efficiencies, things like chopping duty cycles, all that stuff is integrated into even the best case scenarios here. And same kind of thing we had to do, of course, with Spica and Origins as we went through these real concept developments. The baseline includes additional margins as you might use nowadays in the Explorer type program, which we think this is kind of a Explorer-esque competition that we're entering. Okay, so point source sensitivity, mapping speed for spectral lines, and then this one here in the center of the bottom is the surface brightness sensitivity. So this is for looking at, for example, low column density gas, cooling lines from galaxy outskirts. This surface brightness sensitivity is independent of the telescope aperture. The other sensitivities are looking at point source, mapping and measuring point sources, so they do depend on the telescope aperture. So telescope aperture is something we're including in our trade. Goes along with detector sensitivity, to basically create the capability that we have. Okay, so one thing I didn't talk too much about last week, so I want to touch on today is high resolution spectroscopy with PRIMA. This is something we're very keen on. It's going to be a driving requirement for our mission. And here you see one, perhaps the preeminent motivation for this, and that is studying planet-forming disks. And I know Meredith is going to talk more about this after me, so I don't want to say too much. This figure was provided by Klaus. I'm confident for the Origins study, I believe. And what you see, I think we've heard about this in other presentations already, a rich spectrum, mostly water, most of these water lines come from the region inside the snow line, but there are some lower temperature lines which come from outside the snow line. Meredith probably described that. But additionally, there's a hydrogen deuteride ground state transition at 112 microns, and that we believe is a powerful measure of disk gas mass, something that is very hard to measure otherwise. This shows our envisioned band, so of course covering this fantastic region. Now, how much R do we really need? That's a key question for all these probes. How much resolving power do we really need? And it's driven by two things, in my opinion, and I'm happy to hear other folks chime in, but there are two reasons you need high resolving power. Line confusion. This spectrum has all kinds of water lines in it, and they're isotopes. And so you want to be able to measure and tell which line is which and measure the continuum between them. That's line confusion. The other is calibrating the continuum. So ripples in the continuum, uncertainty in the continuum. If the bins are larger, that results in a larger net uncertainty in your extracted flux. So we're looking hard at this. We don't have a final answer, but we think the answer is around 5,000 is a good place to be. And from my standpoint, from an instrumentation side, that's a number that I think we can actually deliver. Okay, so 5,000 is a number to keep in mind. And you see here some model spectra from Klaus kind of justifying that 5,000 as a really kind of a threshold at which you can really identify these individual lines. And this particular part of the spectrum around 56 microns. Okay, so how are we going to do high resolution mode? There are a couple of ways that we're looking at. We're trading, as Jason said, two approaches to the high resolution capability. So the first is to process the light with a Fourier transform spectrometer on its way in from the telescope to these slip-fed grading modules. And this is the approach that Origins used, that we used for the OSS instrument on Origins. It's also the approach that Spica Safari used in their development of the Safari concept. Although in detail they have some differences, but that basic idea, and you can see here a figure from the OSS study that we did. As the light is coming from the telescope, you pick it off, you collimate it, you send it to the interferometer, and then you insert it back into the train
and through the slits, and then it's processed with the back end gratings and detector leads. So this has some very nice features. First of all, if you set this up right, this single module can cover your entire observatory. It can cover all the bands. So I'm showing here with this circle on the slits, an example field that this FTS might have. And so it can actually, even if you don't align the slits, it can couple, it can process light from all of them and give you this RF 5000 at 112 microns where the HD line is. So this is very promising. The unfortunate aspect of the FTS is that the resolving power is inversely proportional to wavelength. So the longest wavelengths will suffer. So these water lines that folks are interested in at the long wavelengths, you're not going to, the resolving power is going to drop off. Okay, and that's unavoidable with this kind of architecture. It has the benefit of putting all the light on the detector, but it's still, the bandwidth on the detector is still set by the grating. So you have a nice low NEP provided by the grating. And then each little grating channel has its own little interferogram. You stitch that together to make a high resolution spectrum. So this is promising. Another approach that we're trading with this is to use etalons. And Gordon Stacy is going to talk about etalons on Friday. Etalon is a more elegant, more compact approach to a high resolution capability. And here you see one of the Stacy group etalons built for Hermes up here in the upper left. This is far better than what we need for Prima. This in the bottom left here is an example of an etalon used on ISO, the infrared space observatory. So there's heritage here. The benefits of the etalon are you can have this long wavelength, high resolving power because you're gonna have a compact path folding etalon of the long wavelengths. The FTS couldn't do that. So you do have to scan the etalon, and so there's a penalty for scanning when the sources are faint. When the sources are bright, you win that back in sensitivity. Okay, so just kind of highlighting these approaches and the heritage that both of these approaches have, it really boils down to just a trade. There's no real technology development or technology risks here. All right, so let's talk a little bit about, sorry about this figure, don't take it too seriously. This shows you the sensitivities of these various approaches. And we don't need to go through the details, but again, we have the best case, or let's say the best estimate, which is the dashes, which are always lower and better. And then we have the solid lines, which are the kind of most conservative margined sensitivities. And so you don't need to follow all these curves. I think maybe you can see that the FTS does a little better because of the scanning penalty, generally, except for bright sources that the etalon can recover some of that. But the point of this is to compare it a little bit with what you might do with other high resolution approaches that we have considered and sort of ruled out. So the first thing you might ask is, what about a Heterodyne system? Heterodyne spectrometer is the only way to get really high resolving power and resolve Doppler information in sourcing. So that is a particular science driver. It's going to be hard for Prima to do that. So that's something. The question is, how would that look in terms of sensitivity? So here's a figure showing a very optimistic Heterodyne receiver, which is 2 times the quantum limit. These kinds of sensitivities have not been achieved yet, at least not at the short wavelengths where you might want to, for example, study HD. A more realistic number might be something like 500 Kelvin at 168 microns. And so this is the sensitivity if you take a Heterodyne spectrometer and consider a narrow band, say 3 kilometers per second wide. So if the line's wider than that, you're going to have to add more noise. If it's narrower, you might do a little bit better by comparison. Okay. So that gives you a sense of this. Of course, the Heterodyne work you can do without the cold telescope. You can do this from a balloon, and so or potentially with Sophia, depending on the band. If you want to do water, that's a challenge, I know. Now, another thing we've considered is a VIPA, which is a kind of a variety of an etalon that doesn't require scanning. And that can potentially save you that scanning penalty and offers potential advantages. The unfortunate part about the VIPA, it's fundamentally a narrow band system. So you're not going to get this wideband capability. And by the way, all of these curves assume the time it takes to make the full, to scan to measure the entire spectrum, the entire high resolution spectrum across all the bands. Okay, so both the heterodyne and the LIGO would not give you that full band capability. They can offer capabilities in narrow bands typically. Okay, so I'm about done. I'm gonna just touch on detectors and then we can have a discussion. So of course, everything hinges on detectors. And as we have all said, this is something we have to build ourselves in this business. So we've been working hard on that. JPL has invested, NASA and NIST have invested over the last few decades, and there's been a lot of tremendous progress. Here you see kind of something that's been around for a while. These are the microwave background TES bolometer arrays that come out of the American devices out of JPL. They're fantastic. This has 512 total pixels. That's nice. It works well. There's all kinds of systematics worked out for these things. Prima, however, or all these probes really need more sensitive detectors. So what you see in the upper right there is our development of transition instance bolometers, which have lower noise equivalent power, more sensitive devices. And these are basically meeting the 1 × 10⁻¹9 watts per hertz sensitivities. Johanna showed some of this yesterday. And so that's one potential avenue. These bolometers, however, while they are something that we're looking at, are not going to enable the huge pixel counts that we really want for Prima and presumably for the other probes. For that, I've lost a slide. Oh, there's the slide. For that, we want to use kinetic inductance detectors. So we've heard a lot about this. We're going to hear more about this tomorrow. So I'm going to point you to Rainer Jansson's talk tomorrow morning, and I think Jordan Wheeler will also be talking about KIDS tomorrow. KIDS are a beautiful emerging detector, well, not emerging anymore, but they have emerged as an extremely powerful way to field large arrays. And the challenge for us in the far infrared space business is to adapt these again to the sensitivities for flight. And so Rainer will tell you more about how KIDS work and show you some examples, dig into that a little bit, but I'll highlight here a result on the right from our colleagues at Epsilon who are working with us on Prima, where they've demonstrated sensitivities which exceed our most ambitious requirements. Okay, so here you see noise equivalent power as a function of audio frequency, and 10⁻19 is here. So those curves that I showed you, the most optimistic assumed 1.1 times 10⁻19. This is already beating that and beating it by a substantial amount at the higher frequencies. Now the source of the excess here at low frequencies, which again exceeds our requirement, is not fundamental, can be improved. And so, there's some improvements further to be had here. And as Rainer will describe, these arrays have also been fielded both from ours at JPL, the NIST folks, and the Epsilon folks in large arrays. And there's even been some flight qualification work done on these systems. So this is looking very promising. And so I encourage you to tune in to Rainer's talk tomorrow. So finally, I'll just note the imaging. I didn't mean to give the imaging short shrift. We're interested in imaging. And in fact, we're collaborating with the Europeans on an imager for Prima. We're talking very seriously with them, and they've indicated interest in providing an imager. Imaging with the cryogenic telescope is fantastic for a few things. You can envision, as was proposed in GEP, to do this photometric narrowband imaging, and you can measure redshifts with the aromatic features this way. As I said, you can resolve the cosmic infrared background at 70 microns, so that's in and of itself, spectroscopy, that's fantastic. It's excellent because it's so fast, for studying time variability of accretion in photostellar systems. So that's something you can do with an imager. And finally, of course, you can do polarimetry. As Jason indicated, the cost to do polarimetry is modest in terms of sensitivity. Making single pole detectors. In fact, some of these detectors are naturally single polarization. So you can build a polarimeter simply by designing, by rotating the orientations of the detectors in some cases to some degree of fidelity. So that's something we're looking at actively. And I think I will wrap up and take some questions. Thank you.
questions from that? All right, say woo. Give it a pink shirt.
Hey, thanks for the nice overview. I just had a question about the detectors and roughly what size a pixel needs to be. And if it's an array, what's the building fraction you would like to have?
Yeah, that's a great question. So we're targeting pixel pitches on the order of a 0.5 millimeter. And we'd like to fill as much of the electrical, we can say electrical filament, we'd like to fill as much of the focal plane as we could in an array which has, say 8,000 pixels. And there'll be multiple arrays like that. That's what we're looking at. Now we understand, of course, you're not going to get, some of these are lens coupled arrays, we're looking at more coupled arrays. It's not going to be like a CCD camera where any pixel, any photon that falls on that thing is absorbed. But we aim to have numbers like 50, 60, 70% of that sort of effective absorption. That makes sense. Yes,
Matt, on that, on the blocks back.
Here, wait.
A couple of blocks back, what are you asking about NEP? And what was the spectral? No, you went back. Maybe we can come back.
The fact sheet?
Yeah, fact sheet, yeah.
Yeah, so these are all low res mode. So that's R of 200. And the detector NEP is assumed are 1.1 times 10 to the minus 19 and 2 times 10 to the minus 19. So both of those, we're below that now for, below even the best case now for the detector. And then, as I said, there's other factors that go into this. There's margin built into what we call the baseline. There's additional margin built in.
Your high R case with Echelon.
Same assumptions. The grading backend has R of 200. And then this is, so for example, here I'm assuming that the Echelon has a finesse of 15, order of 130, and there's an efficiency associated with that Echelon, and then you've got to scan it, right? So all that's folded in. And there's the, but it's the same telescope area, same instrument, same detector NEP between the dash and the solid. Does that make sense?
Yeah.
Okay, I think we're about in time.
Take one more question while I set up my thoughts, but then I think we better.
Okay, yes, that's right. We can take one short, concise question.
Hey, Matt, I have a quick question. So I'm not understanding, give the detector NEP of 10 minus 19, and then what's the background after the detector? Is it same order or is it? Maybe a stupid question.
Yeah, so I didn't show that. So this takes in the diagonal light background, through the instrument, any background from the telescope. There is some, I think when I do the FTS, there's an assumption of some additional background from the FTS. But not from the short one, because I can go with that, right? So there's not, so that's why we're pulling the gradings to Kelvin. There shouldn't be any background from the instrument.
Okay, but the detector, the system is not background limited at tomorrow.
That's right. The system, right. So thank you. The system is close, the 1.1 is close to background limited R2, but not quite there. Right? So we would benefit from that extra factor of 3 that the astronomical detectors are showing. You benefit about a factor of 2 to look at this for origin. Now, the 2, 10 minus 19, that's totally not background, but that's detector noise limited.
Okay, everyone give another round of applause. Thank you. We're looking at the schedule, we are a touch behind, so we're just going to eat into that small group workshop time. Okay. All right, so next up is Meredith McGregor from the University of Colorado Boulder.
Hopefully this works. Okay, let's see if I can use the mic. Hi, everybody. So I am going to, you've heard me speak a lot so far, but I'm going to take my IR STIG co-chair hat off and talk to you about science and sort of my science interests and expertise and try and put that in the context of this probe discussion that we've been having so far today. So I think basically every probe concept that we have heard about so far has talked about planet formation and circumstellar disks and why we want to understand exoplanets, how they formed, how they evolved, what makes them habitable. And I can't decide whether it would have been better that I went first so that I could have motivated why everybody wants to talk about planet formation, or that it's appropriate that I'm coming now so we can sort of bring this back together and really go back to the science, talk about what we know in planet formation, what we don't know yet, and what we actually need to do to answer those questions. So that's how I'm going to structure my talk today. So it's going to very much go between what is the state of the art that we have now, and what do we actually still want to know, and what do we need in order to do that. Okay, so before I launch into the detailed science questions, I'm going to start with the primer of planet formation so that we all are actually on the same page, because there's not a whole ton of people who are passionate about planet formation in the room. This is our general picture of how we form planets and habitable planets, right? We start with a molecular cloud. We form our young stars. Those stars are surrounded by these disks of dust and gas that we call protoplanetary disks, right? That's the stage that we think we have enough material to form giant planets. This lasts for somewhere on the order of 1 to 10 million years. That's a big error bar on age. We can delve into why that is. And eventually we clear most of the material away, and what we're left with is our main sequence star, any planets that we happen to form, and this kind of remnant dust disk, what we call debris disk, which you can think of just like our own asteroid belt and Kuiper belt, right? These are comets and asteroids populating these remnant debris disks. Okay, so planet formation has really come into its own as a field in the last decade, I would say. It's become increasingly popular, and a lot of the credit to that has to go to ALMA, right? Because ALMA came along and we stopped looking at blobs and trying to imagine how we formed planets from them. And we started seeing these beautiful images of disks, right? Now we can actually look at the environments that planets are forming, and we can resolve them, and we can think about what kind of planets might actually even be forming in these gaps. So the left side of this plot, all of these are these protoplanetary disks, younger systems. So think of these as things that are less than 10 million years old. And every single one of these has detailed structure in them. The right side of the plot, these are our debris disks, right? These are our more evolved systems. They also have a lot of structure. We see double rings, we see Fomalhaut. This is an ALMA image. Dave showed the Herschel image of Fomalhaut earlier, which has this kind of eccentric shape, which we think could be getting carved by a planet. Okay, so we can see these things, and we can start to imagine the planets that might be forming in these gaps, and I can run in-body simulations, and I can tell you, like, maybe this gap is being carved out by a 0.2 Jupiter mass planet. But now I think we want to go beyond that, right? We want to step past just imagining these planets. And I have to show this slide, which I'm not going to have enough time to go into, but will hopefully motivate, why we need to do more than just image things, right? Disks are a complicated place. This is a very complicated figure. The left-hand side here is kind of showing you the schematic in gray of a protoplanetary disk, where we have this flared structure and what's called the midplane, the middle line of the disk. Here's our debris disk, right? Thinner on the right. Overlaid on here are things like the C to O ratio, right? Different stages in the disk where different things are freezing out, ice lines, right? For different molecules. This is trying to show you where different instruments might probe in the disk. And it's also telling you what grain sizes you might probe, because when I pick a given instrument to go look at a planet forming disks, I'm actually probing many different things. I'm probing different temperature regions in the disk. Shorter wavelengths get me closer to the star. Longer wavelengths like ALMA get me further out in these carbon belt regions. But they're also sensitive to different grain sizes. So now with something like IRSTIG, I'm looking at tiny micron-sized grains. Something like ALMA, I'm looking at things that are more like a millimeter to a centimeter. And I'm probing different molecules, right? So every different telescope I pick is now conflating all those different properties, and it's probing different parts of that parameter space that I might want to get at. What I like to argue is that we're missing a lot of information by not having the far infrared here. We're missing a lot of molecules. We're missing a range of area here that we might be probing at disks. We're missing tons of different opportunities. And so from the side of planet formation, I think the far infrared is critical, right? It opens up this completely new regime that we can try and understand these systems. So let's walk through that. So Asantha already showed this earlier in the day, because I am structuring this, these are some of the big science questions that we've been talking about for first. And I'm focusing on the first two that Santa skipped over. So the first, right, is what is the origin and evolution of planet-forming disks? And the second is what is the trail of water from molecular clouds to oceans? But now I've split these out into sub-questions. Right, so I have 3 sub-questions for each of these because that's like a really big question to say, I want to understand the water trail. What does that actually mean to do in terms of scientific questions? So let's break this down into these 3 questions for each, right? How many disks have enough mass to form a Jupiter? Does planet formation have to be fast or can it actually be slower? And what is the origin of gas in our more evolved systems? And for that next question, how does the ISM environment maybe impact water formation? What is the actual origin of the water we see in these planet-forming disks? And how did Earth actually end up with the water that we have here? So the rest of my talk is going to step through each of these sort of 6 sub-questions and give you the state of the art of what we know now, and then what I think the bar infrared can do for us to answer that. So let's start with disk masses, right? We want to know, do planetary disks have enough material to actually form a Jupiter? Okay, so the state of the art comes from ALMA here, right? On the left is showing a plot that's giving you fraction of disks that have a mass above a certain amount, and then dust mass, and they're stepping through different star forming regions. So the brown line here is Perseus, which we think is a little less than 1 million years old. And then you can step all the way through an age to Upper SCO, which is the green, that's 5 to 11 million years old. Some general takeaways, right? Disk masses decline as we age. That makes sense, right? We're losing material from these disks. And I've put a purple line here to sort of draw your eye to something. These are dust masses, so this is just dust. We're ignoring gas right now. But this purple line is the mass of Jupiter, 318 Earth masses. So anything above to the right here is more massive than Jupiter in terms of dust mass. Anything to the left is less mass than Jupiter in that disk in dust. That might bother you a little bit, right? Okay, most of these disks are much more mass than that. Now I can win by, Jupiter is a gas giant, right? So I put gas in the system. So this is now showing you CO gas to dust ratios. How much CO gas do you have relative to the dust? The ISM, we always assume is 10. If we actually try and measure this in disks, 100, sorry, we get something closer to 10, that's skipping ahead. So maybe you get an extra factor of 10 here. But there generally still seems to be a mass problem, right? We don't have enough mass in these disks, and we're losing the mass very quickly. Well, obviously we form Jupiters, right? We have a Jupiter in our solar system. There's giant planets in other planetary systems. So maybe we're just messing this up, right? Maybe we don't actually understand disk masses that well. Okay, and I think there's a very strong argument to say that we don't understand disk masses that well. And if I want to talk to you about planet formation and how I form a Jupiter and how long I have to actually do that, I need to get the disk masses right, and I don't think we have that right now. So I can't actually get up here and tell you this grand story about how quickly we form Jupiter mass planets because we can't answer it right now. And this is where we get to HD. So this is a lovely plot that came from a review paper that's part of the Protozoics and Planets. It just got published by Anna Meteorites. The bottom, these are all disk masses measured using different things, different tracers for Heliohydra. So this is one system. And these are all the different masses that have been derived for that one disk. And they span from 10 to the minus 3 here to 10 to the minus 1, so orders of magnitude. Everything in the bottom is derived using some tracer, like dust to gas mass ratios, or measuring different CO isotopal logs and trying to then infer CO as a tracer of hydrogen and scale to get a disk mass. So these span a huge range here, and there's a lot of problems that we could point to different things, right? Like 12CO is well known to be optically thick in disks, so if I measure 12CO, I don't get the whole disk mass. You can go to other isotopal logs that are, like less optically thick or more optically thin, but maybe we don't actually know the CO to H2 ratio that well at all anyway, so it doesn't matter whether it's optically thin or thick. I'm still not actually getting a good estimate. Everything on the top is measured with HD, which we've already heard about. And there's still some spread here, but it's a lot better because we think that we understand the chemistry of HD quite a bit more. So if we really want to weigh disks, we should try and use HD, and we should actually try and resolve that line and do it for a statistical sample of disks over a wide range of ages so we get disk masses. Okay, we've already heard these lines. There's 2 lines of HD. They're at 112 microns and 56 microns. I would argue that to do this well, we need much higher spectral resolution. We need something more of like 10 to the 5, because this is going to allow us to actually resolve these lines and get accurate disk masses out. Next science case. Let's talk about disk evolution. Okay, so maybe we get the masses right. Now we want to know how long do we actually have that mass in disks in order to actually form our planets. So ALMA has done great work here too. This is IR STIG. It's a system that's about 500,000 years old, and you can already see gaps in this disk. This is what we classify as a class 1 disk. So it's actually still in this stage where it has an envelope falling onto the disk. So it's very young, and we see gaps. And if you think of those gaps are coming from planets, then planet formation must start very early. But when does it actually end, right? We don't actually know how long we have this material. Do we have to form all of our planets within 500,000 years? Or do we actually have longer? Do these disks last for longer? Now, the main way we remove material from planet-forming disks is through a process called photoevaporation, where the high energy radiation from the protostar actually irradiates the upper layers of this disk and it strips material away in a photoevaporative wind. This is how we lose material from disks. So if you want to know how long disks last, you actually need to understand photoevaporation, which means we need to get a better handle on this, right? So this is actually an area where models are very degenerate because we don't have good measurements of the EUV, FUV, and X-ray flux from protostars. And that sets the timescales for this photoevaporative flow. Now, we could try and go measure that, but we can't actually measure EUV fluxes. And another way to answer this question is actually to measure the lines of oxygen, O1 and O3, that are being produced from this photoevaporative wind from the disk. So O1's at 63 microns, O3's at 52 microns. Again, we need pretty high spectral resolution to do this, something like 10 to the 5. And in this case, these are showing predicted line fluxes for oxygen 1. So this is that 63 micron line. And this is showing the flux in O1 compared to the X-ray flux. And then these are different models of different UV fluxes, in the different colors. So depending upon, what I measure from the flux of O1, I'm actually able to break some of these degeneracies, get the X-ray and the UV luminosities back, and then now tell you kind of what the timescales might be in order to evaporate these disks. Okay, moving on to the more evolved disks. This is a nice plot from Meredith Hughes' review paper from a couple of years ago, which shows the state-of-the-art of gas in debris disks. And if you'd asked me a decade ago, I would have told you don't actually think there's any gas in debris disks at all. And now that's wrong. We're measuring gas in debris disks. Almost all of it is CO. So the orange here are the detections, right? And these are young, which is less than 50 million years old versus old, and separating out different spectral type stars. So we've detected gas in debris disks. It's still a relatively small number. It's almost all CO, it's almost all around young sources, and it's almost all around A-type stars. So really hot, massive stars. O1 and C2 here, I can see we have 3 detections of O1 in debris disks, and we have 5 detections of C2. And one of the big questions here is we don't actually know how we're getting this gas in these old systems. When I go and I see a disk that's 1 billion years old, where is that gas coming from? Is it somehow primordial where it's being protected in some way and like hanging out here and lasting for 1 billion years? Or is this coming from cometary collisions like we imagine comets colliding in our own solar system outgassing material? We'd like to understand that. And there's actually a lever here to understand that in the far infrared. So the model is actually that CO doesn't last for very long because it gets photodissociated by this high energy radiation from the star. So I would expect my CO reservoir to quickly become carbon and oxygen because it's getting photodissociated. And if that keeps progressing, I wouldn't see CO at all. So if you say that I'm actually observing CO in a disk, then it has to possibly be protected. And one way to do that is to have the CO get photodissociated. You have your C and O that actually now viscously spread in your disk, and they protect the CO. They shield it from being photodissociated. So you can actually follow this through and come up with different scenarios of how much carbon and oxygen you would expect to observe in a debris disk, depending upon the scenario in terms of the ratio of CO versus now split carbon and oxygen, depending upon whether it's being in this kind of self-shielding scenario or not, right? And again, these lines are in our far IR, right? O1 is at 53 microns, C2 is at 158. High resolution in order to actually, resolve all of these lines at the sort of 3 to 5 kilometer per second regime that we think is in these disks. And this is now a prediction of what the C2 mass should be for different debris disks. The red line is Herschel. This is a 10-meter for IR telescope, and the yellow is something like Spica or Safari. And you can see, Herschel wouldn't have observed this pretty much at all. There's no disks above the Herschel line, right? We don't actually think that any of these debris disks have enough mass in C2 to have been able to detect them. But if we drop down to sort of this level, right? Like a 2.5 meter cryogenic space probe, all of a sudden we're getting something on the order of 20 to 30 disks where we can actually, for the first time measure not the 2 C2 detections that I just showed you, but 30. Okay, so I'm going to move to water now and highlight a few things that we can think about with water. So you often see this picture, which is the sort of trail of water, right? The idea that water comes from our interstellar medium is inherited into protostars, which then, is inherited into our protoplanetary disks, and then the remnant material that we see in our debris disks and solar system bodies is, following this trail all the way through. So we're taking the same reservoir of water, and we're sort of inheriting that chemistry through the entire process. We don't actually know that that's the case, right? We don't actually know that the chemistry follows in this linear fashion, or if some of this chemistry is actually disrupted, maybe the water gets destroyed somewhere on this path, and now we're regenerating water in our protoplanetary disks, right? This is the idea of something like an inheritance scenario versus a reset. Does the chemistry reset where we're in these protoplanetary disks? Now, we've already heard this, but I'm emphasizing it again, right? We really need a space telescope to do water well. This is a narrow chunk of our far infrared spectrum, and it's highlighting just one of these lines of water. This is the 538 micron water line. And this is showing the blue is Sophia, atmospheric transmission at 13 kilometers, and the green is ALMA. And in this line, there's no atmospheric transmission at anything there, right? If you want to measure this line, you have to go to space. Okay, so this is the same figure that you've already seen that's showing the kind of wealth of water that we might see in the far infrared. This is from the Origins report, right? Showing the different water lines running from 10 microns out to 538 microns. This is that same line here. Here's our 179 micron line. These purple regions I want to highlight here are the ice features, right? So this is very different. These are broad. And we don't actually know that much about water really at all. We haven't detected that much water in disks or star-forming regions or anything. So this whole question of is this inherited chemistry versus is this reset chemistry is something that's open to be answered. And as a general statement, Herschel actually sort of found water to be quote unquote missing compared to what we'd expect it to be in interstellar medium, right? So if we took what we think we know about the interstellar medium and we assume that that's the same for protoplanetary disks, Herschel actually detected less water than we might have expected it should have. So clearly there's something going on here. One possibility is that it's locked up into ice and that we actually, have more water locked in the midplanet ice. So that would further emphasize why we need to look for both gaseous water, right, and also these ice features. So to do that, right, there's a wealth of lines here that span anything between 32 and 538 microns. Generally, to do water and to do this sort of tomography, to actually map these lines in Doppler, we need really high resolution, right? Now we're talking about something like 10 to the 6. And then, noting the ice, right? There's ice features at 45 and 63 microns, which are these dark purple things. We don't need high resolution for that, but they're also important in the spectrum, and to really understand this picture, we need to do both. And then to tie this all the way back to the solar system, right? We want to know how our water got to Earth. Earth formed within the water snowline of our solar system, which is actually out at 2.7 AU. We're at 1 AU. So somehow our water has to have gotten delivered to Earth. So this is where, this is showing your typical D to H ratio, right? For different bodies. This is the protostellar nebula down here at the bottom. Here's Earth. Here's the line for Earth. And these are asteroids, Enceladus, and various comets, right? These are Oort cloud comets. These are Jupiter family comets in the Light Peak. kind of trying to compare the D to H ratios for these different bodies and use that as a fingerprint, essentially, to say, you know, if I match the D to H ratio, maybe that's where my water came from, right? So if you look at this, you would argue that asteroids look a bit more similar to Earth. These sort of Oort family comets have higher D to H ratios. Maybe these Jupiter family comets, for which we only have one measurement and one upper limit, match. But we would like to do more of this in the solar system in order to really understand where Earth's water came from. And then to do that, you need to pair these two lines, right? You need the water line at 243 microns and HGO, deuterated water, here at 234.6 microns. And again, these are water lines, so to do this science case and to be able to resolve these lines well, you're looking at something like 10 to the 6 in spectral resolution, so very high spectral resolving power. Okay. So that's my run through of protoplanetary and, you know, solar system and free disk science cases. And then, you know, if we take that standpoint where we start from the science, right? We say, understanding the origins of planetary systems, how they inherit water and how that makes them habitable planets is important and exciting science to do. What does that tell us we need to build in terms of a space telescope? What instrumentation do we need to do to enable that? And so I would argue that in order to do those two questions and to do them well, we need a far infrared space probe that's enabled to have high spectral resolving power. Because if I follow this through from wanting to answer these two questions, breaking it down into particular lines and particular velocities and resolutions that's required, that's where my flow of thought ends up. And so then something like FIRST, which is really kind of trying to focus on spectroscopy in this full range, would enable something like that. And with that, I'm happy to answer any questions. And I'll also note I have flyers for FIRST, you know, fancy new fact sheet with my amazing graphic design skills. So if you're interested in learning more, then please come grab one and talk to me.
Any questions for Meredith? Thomas? Mary? Okay.
Very nice talk. Thank you very much. I think you got really to the core of the questions. And so you mentioned that for measuring actually the mass of the disks, you would like to have the HD line velocity resolved. And so can you elaborate? I assume, I mean, I'm not an expert, but I assume it's optically thin, right? So can you elaborate on how much more accuracy you can achieve if you have it with velocity resolved instead of just measuring the integrated line flux with low resolution? Yeah,
that's a good question. So if I scooch back to HD, it is optically thin. The like general velocities that we think we would need in these disks is something on the order of like 3 kilometers per second. And that is to be able to do, you know, your average protoplanetary disk at 150 parsecs. We would expect the sort of spread of that line to, you know, that to resolve 3 kilometers per second, then it's sort of not phrasing this badly. We're motivating that based upon, like, if we want to do distant star forming regions, right, at 150 parsecs, what line resolution do we need to resolve something that's a 3 kilometer per second operation? So that gives you, you know, roughly a spectral resolving power of 10 to the 4 to 10 to the 5 to be able to do this for a larger range of more distant systems. And what we've been really talking about as a group is actually trying to do this at different ages. So really targeting these different star forming regions so that you can measure HD accurately for populations of disks that are, say, 1 million years, 3, 5, 10, right? So that you actually can do a statistically significant sample of, you know, tens of disks in each sort of age bracket, with the goal of then motivating this disk evolution question. So we could really accurately measure disk masses for disks that span this whole age range, we could make these sorts of plots more accurately where we're looking at how disk mass evolves. And so it's really more of an argument of, you know, in order to do this for these more distant regions, how much spectral resolving power do you need to actually detect this light, right? It's a different question than like it's like this for 10 disks that are the easiest ones that are the closest that are nearby. Does that help?
Any question for the author?
Slide back.
Which direction?
HD.
This one.
Is that the same? It's a single data set, right? On HD or different data sets.
I'd have to actually go back and look at that. I believe it's all the same data set, but it's using different, I mean, you still have to assume like that we think the bulk mass of disks is hydrogen, right? And so we can't measure hydrogen. So every single one of these is trying to piggyback. I measure something and then I try to get a hydrogen mass. And so some of these are using like different D to H ratios to try and like extrapolate that in different, you know, baseline assumptions. So there's some spread even in HD. Somebody want to, Gary wants to.
With regard to that last question, I think all of this was obtained by measurement we made with Herschel for the end of the mission. And the spread is probably as you suggested. But I was going to say, partially in defense of some work we've done in the past, that I think we understand the water story pretty well. It's pretty consistent in the interstellar medium. The SWAS mission, which was an explorer in the late 90s, which looked at molecular oxygen and gas phase water, is all consistent with gas phase water being a surface tracer, and essentially in a PDR. And the absence of any molecular oxygen suggests that the bulk of the oxygen in these clouds is locked in ice. And the follow-on, the bookend to that is we're working on a mission now, Spherex, which will look at the 0.75 to 5 micron spectra at a resolution sufficient to resolve these broad ice features, in particular the 3.05 micron water ice feature. And we'll look at hundreds of thousands of protoplanetary disks in that feature. But you put your finger on the unknown that these missions can help with. A mission that can go beyond what's been done in the past in terms of looking at multiple water transitions, as well as ice out in I'll say the far infrared. One of the problems with the ice features in the near infrared is that for low inclination planetary protoplanetary disks, things are very optically thick, and a lot of this radiation is scattered. So interpreting the data requires an immense amount of radiation transfer analysis. But when you get out to the 40 to 50 micron region, I think it becomes much more straightforward to infer the ice content. So after all of that, I think we'll then be able to address this question you put your finger on, which is, are all of these, decade to 2 decade chemical models of protoplanetary disks based on the right initial assumption? And that is, you start with the assumption of the parent cloud composition, or as you suggest as a possibility, are things reset? In which case you end up with different outcomes, depending on what you assume. And a well-constructed far infrared mission should be able to answer that.
Yeah, that's an excellent point. Thanks, Gary.
Any question from Morris?
Yeah, so for the HD question, because as far as I understand, another experiment is about the situation is very dependent on the physical conditions you're at. So how big of an uncertainty factor would you expect for the mass estimate? And are there, for example, complementary observations that would help you with the chemical models to constrain the duration fraction to a specific part of this?
Yes, so that's it. Yes. So you're saying that, the amount of deuteration of the material in these disks is a model dependent and condition dependent factor as well, right? Which then folds into this I can't stand up here and say that it's going to be magic. We can measure HD and we know the disk masses, right? There is clearly still a lot of uncertainty in that. Obviously, I can extrapolate and say it'd be great if we could measure D to H ratios in disks, because then I'm starting to actually measure that deuteration factor, right? Usually people assume something, either the D to H ratio that's the same as the interstellar medium, or maybe you assume the D to H ratio from solar system measurements, but you're assuming something. And if we could actually measure D to H in disks, then we can measure that directly and fold that in. I have not actually thought through that, as well. We thought through it more for the solar system case, but we're going to be targeting HDL and water simultaneously in many systems, hopefully.
Michael, the question I have is, are you able to run computer simulations to get an idea of how much mass it does you need to form a Jupiter sized planet?
Yes, people absolutely try and do those simulations, yes. And Jens is pointing out that I'm talking way too long. Yes, so there's a wealth of simulation work that gets done to try and understand how planet formation happens. We've been working, I'll flip that around in terms of like what we want to do here, in that, given the sensitivities that we've been seeing, these like 1 × 10⁻⁹ sensitivities, we'd expect that with something like FIRST, we could measure in a reasonable, an hour or something, down to like a Saturn mass of material. And so that gets us below that limit, right? And so then that sets this kind of barrier that we can actually start to probe these sorts of masses we've been talking about, these giant smaller masses below that. But there's a lot of complications in terms of how much material we need to form this, in terms of fluid, sticking of grains. If you have more ice, things stick better, and you can form things faster. And so that's an entirely active area of model. Not my expertise, but many people's.
Actually, what is possible this time?
There's not. I'm sorry, guys.
There
wasn't time quite for the last question, so we're going to have to move on to the more workshops. But everyone, let's thank Meredith one more time. 5 minutes for small workshop. So I already sent an email out to everyone. We'll on the back of your badges coming from Thursday. Again, there'll be 3, 4, 5 in here, and then 1 and 2 breakout rooms. So take a look, remember, move to your respective locations within the next 2 seconds.
So the cookies will be delivered around 3:15, and we'll reconvene at 3:40. So feel free to keep working through the normal coffee break. Yeah. Straight lines, just kidding.
For the most part, you just want to look that they're okay.
I just want to make sure they look okay and all the things.
Well, on the bright side, if they're not, it's too late to change it, right?
So I'm gonna get this. It's gonna be this, right? Yeah.
It's gonna be
Because I'm not gonna get the
modulo.
right.
Yeah, it's gonna be exactly the same as what's up there, and then you just have to click on here, and then you can use this guy Maybe. Except someone turn it off.
Okay,
Go through your slide like that. Oh, man, you have animations.
exactly. That's why I want to make sure they work.
All right.
Okay.
Are we still sharing our screen?
Stop. Yes, we are.
Sorry, everyone.
There we go. Okay.
Okey-dokey.
Yeah. Are we still recording?
Yeah, are we still recording?
Audio,
Oh.
and there's no video in the.
Oh, good. And click.
I just clicked. You're good.
All right. This is now yours.
The power.
That's my cue. So usually it's best if you just click this on like your lapel.
All right, you want to go for it?
Testing. That sounds great. All right, everyone, hopefully you're in your seats now. Maybe. All right, so we have a little bit of an ambitious schedule over the next hour and a half, hour and 20 minutes. Before the bus is here, we have to leave for the social event. So we're going to go ahead and start. Click your cams open right now before Kevin starts speaking. We have Kevin Stevenson here from Johns Hopkins EPL. He's going to be talking about using planetary infrared access to study the nearest potentially habitable exoplanets. I'll get the ones.
All right, cool. All right, thank you for the introduction. I'm going to sort of ease us back into the science side of things. Like you are all eating and drinking and conversing. I want you guys also to imagine a very bright and exciting future. Let's say, 2035. And in this exciting future, we have a far infrared probe that has launched as of 2032. It has acquired a lot of amazing science. There have been many press releases about the earliest galaxies, about the study of protoplanetary disks. And there's also another announcement. A full 10 years before a NUVEX mission is ready to launch, the FAR IR probe is announcing the first detection of biosignatures around the nearby. This is not science fiction. This could be true. All we need is a mid-infrared, broad wavelength, low resolution spectrograph on a far infrared probe for this to happen. So I'm going to talk to you about planetary infrared excess, or PI for short. And this new method of characterizing exoplanets should allow us to study the nearest potentially habitable planets, such as Proxen b, a planet that is in the habitable zone around the nearest star. All right, before we dish out a slice of pie, let me go into some of the big three questions of astrophysics. They are, of course, how does the universe work? How did we get here? Are we alone? Now, I really feel that any large astrophysics mission should strive towards answering these three questions. And based off of the science that I've seen over the last couple of days here, I really think we've hit or nailed these first two questions really well. All right. And so I'm going to try to focus on this third question, are we alone, in the context of a FAR IR probe mission. And to do that, I want to take a look at first this exoplanet mission arc. These are the exoplanet-related missions, those that can both detect and characterize these exoplanets. And I want to focus in on sort of the history of where we've been at so far. In the first couple of decades of exoplanet characterization, we've been using Hubble and Spitzer to study hot Jupiters, right? These Jupiter-sized planets, really short in-orbital periods. And we've sort of honed our craft as to what that might look like. We've been doing transits, eclipses, phase curve observations, mainly with these two telescopes. And of course, what we're looking forward to the next decade is the James Webb Space Telescope. This is really our first opportunity to hone in on rocky planets orbiting M-dwarf stars.
Okay, there is a lot of huge opportunity here, for example, with the TRAPPIST-1 system to study the planets for the first time. They're in the habitable zone, to measure their atmospheres, to see whether or not they even have atmospheres. Maybe we could even determine their surface temperatures to see if they are compatible with liquid water. Well, where do we go from there? Well, we're not really sure what's going to happen in the 2030s. They've told us that we will have a HABEX or LUVOIR type mission in 2045 that's looking for Earth-like planets around sun-like stars. But it seems like we've just kind of turned and pivoted 90 degrees and gone off in the opposite direction, putting all this time and energy in the next decade towards studying these M-dwarf planets. And it's just as we're about to actually find life, we're going to turn away. So how do we do that? How do we actually find life with the Far Infrared Probe mission, even though we may not have the photon gathering power of James Webb? Well, really what we're looking for when it comes to detecting habitability is collecting photons. We need something that is a light bucket. And so if the aperture size is smaller, we just need to find brighter targets. And so here I'm showing you a graph of the known M-dwarf planets within 20 parsecs. And what you can see here is that the planets in blue are the non-transiting planets, and the ones in orange are transiting. And it's interesting that the 20 nearest planets from 0 to 7 parsecs, all of them are non-transiting. So really, all we have to do is focus on these non-transiting exoplanets because they are going to be orbiting around the brightest stars. Of course, no one's actually characterized the atmospheres in detail of a non-transiting exoplanet, right? So that's the catch. How do we look at these planets and understand their atmospheric compositions and search for signs of life when we don't have this transit technique and they are too close in to be able to resolve them spatially? All right, so I'm gonna segue a little bit here and talk about different ways of studying bodies, in astrophysics, and tailor it a little bit towards how we do things in exoplanets. So there's basically three different axes, three different ways in which we tend to study astrophysical phenomena. And in order to resolve two bodies, we can do that many different ways. The first axis is spatially resolving two objects, right? This is, for example, right ascension and declination. You see two objects in the sky, you say, okay, there are two stars, perhaps they're binary companions, we can resolve them, no problem. In exoplanets, this is how we have, goes to direct imaging. We want to spatially resolve the planet from the star using a coronagraph to block the light from the star. Now, the other axis that we typically use is time. In this case, this is where the transit exoplanet technique comes into play, where we have the planet crossing in front of and behind the star. And we're using time to enable a differential measurement. We measure the system before the eclipse, during the eclipse, and after the eclipse. And during that eclipse, when the planet has gone in behind the star, we're able to make that differential measurement and say, yes, we know that photons are coming from the planet and at these wavelengths, and this is the composition. Well, there's the third axis here that exoplanets has yet to explore. And many of you will be very familiar with that. That, of course, is the wavelength axis, right? For those of you who study protoplanetary disks, for example, you're very familiar with infrared excess of a new system that pertains to the circumbinary circumstellar disk. And so from a spectroscopy standpoint, it is possible to distinguish a planet from a star just purely looking at a broad wavelength spectrum. So how does this work? This is the planetary infrared excess technique. What we have here is a plot of spectral intensity as a function of wavelength. I'm showing you two black-body curves. One is the first, just a star, 4,400 Kelvin. And the second adds in a planet. It's 1,000 Kelvin. And I've actually magnified it by a factor of 1,000 just so you can see it visually. It looks very much like what you'd expect, infrared excess. Now the catch is that we have to have the right wavelength range in order to measure the reference wavelength where we only have the star. And then of course the remaining wavelengths where we have the star and the planet. And so all we have to do is measure the star itself at those wavelengths and interpolate to those longer wavelengths. Any emission that we measure that's in excess of what we would expect based off of our stellar models can be attributed to the planet. And you'll see if you want more information here, there's 2 publications that we have in AppJL. They go into the gory details of why this is exciting and both hard at the same time. But fundamentally, it is no different than a 2 SED fit for binary stars or circumstellar disks. It's just at much higher precision. Okay, so let's get into biosignatures. What's the right wavelength for detecting signs of life? Well, as it turns out, the mid-infrared is the best place in thermal emission. This is the spectrum of the Earth, and we have in our methane, ozone, carbon dioxide, water, and the peak thermal emission of the Earth is around 10 microns. So this is an ideal range because we get photons from the planet. It's a good planet-to-star contrast ratio, and we have access to biosignatures. So all we need is a little bit of flux from the star below 5 microns, 2.5 to 5 microns should do just fine. And it gets a little bit tricky beyond 20 microns, although there's still planetary flux there, we don't have access to those biosignature molecules that we need to find life. So this is really the sweet spot in the mid-infrared for detecting biosignatures. Now I'm showing you a case study that we did for PROXEN-B. And this is, instead of just the planet flux, like I plotted on the last slide, this is divided by the stellar flux. So it's a planet to star flux ratio. Okay, and you can see the point here is that there really is no planetary flux below 5 microns. So this is a great place to measure the stellar spectrum. And of course, we still have our ozone, CO2, and other features at longer wavelengths. And what we're able to do is to constrain the surface temperature, first of all, of the planet. This black curve is actually indicates the true thermal profile of the Earth, but we are most sensitive to the surface, and that's what we can constrain. So we understand that, yes, the surface of this planet could have liquid water on it, which is great. Then we can constrain its composition. This is here, you probably can't read these specifically. These are molecules, and these are posterior distributions. So you can see that we have Gaussian distributed posteriors, indicating a good constraint on the abundances of these molecules. And I should point out, this study was conducted for an Origins type mission, so 6-meter diameter, using only 10 hours of telescope time. If you think back to direct imaging mission, they're going to need thousands of hours of observations in order to characterize these directly imaged exoplanets. With transits and eclipses, you'll need hundreds of hours to detect biosignatures. Here, because PROXEN is so bright, we can do this in 10 hours. Now, okay, maybe we don't have an Origin style mirror, so let's take a look at a case of a 2-meter diameter, okay? This is case 1, a far IR probe looking at PROXEN-B, 2-meter aperture size, over 100 hours. That's reasonable. Instead of a day, we're looking at 4 days, right? We can do this within a week with overheads. And we're still able to constrain the atmospheric abundances of major molecules within this planet's atmosphere. And just for comparison, we also ran this for James Webb with a similar SNR. And because the mirroring instrument has a more restricted wavelength range, the LRS is 5 to 12 microns, it just isn't able to accomplish what we want. It doesn't have access to the CO2 molecules at 15, or the H2O at 18 plus microns, and it doesn't get a good constraint on the thermal profile. So really, it's this simultaneous broad wavelength coverage that gets us to where we need for biosignature detection. Okay, I'll wrap it up here with reminding everyone, planetary infrared excess, PI, could enable this atmospheric characterization of the nearest exoplanet atmospheres. Okay, this is PROXEN-B and other planets potentially within 10 parsecs of here. This really is the next step after James Webb. After we use the JWST telescope to characterize these atmospheres, determine the most fundamental basic questions of whether or not they have atmospheres, we can actually dive into answering the question of, is there life on these nearby planets? So when you are going about designing your far probe missions, please remember those 3 big questions I had at the start. And hopefully we can address all 3 of them with a single mission. Thank you. I'll take questions.
Good questions, Kevin.
Okay, so this is non-expert comment except for that we're working on calibration. And we use stars for this, we use asteroids and so forth. And the issue with the stars was always, well, they should be easy to extrapolate, but they are not perfect, right? So, and you're talking here about a really, really tiny difference. So I'm sure you studied this question because it is fundamental. Any other question?
Yeah, some of the work we've done is looking at stellar variability and breaking up the star into spectral components, whether it's a space photosphere and components of activity over certain fractions and regions. And we've actually done that for HST observations, where we've been able to infer the spectral components of a star. On top of that, we can actually simultaneously calibrate the sun on a per exposure basis. So because we have access to the pristine, non-contaminated wavelength range, we're actually able to measure the stellar spectrum and how it's varying at those wavelengths, and then apply that to longer wavelengths. We're actually going to, on top of that, be testing this method with JWST data. It's actually really helpful to have a planet that does transit as a means of testing, because you have the secondary clips. So you have the uncontaminated stellar spectrum at all wavelengths. And then we're going to be applying this technique as if we didn't know the planet was transiting, to then pull out the correct information. So there are steps along the way to get us there. It's not, it's not the easiest path, but I don't see any major showstoppers with that.
Okay, yeah, one common question. So a comment, how is there a fourth axis of polarization? And just following that, you could possibly, for fast things that are orbiting quickly, you can use polarization as a way of measuring the reflected starlight, right? Separating that from the emission. And the second question is, what about large planets? What about detecting excess from, cold but big planets around things? Is that, have you looked at that at a longer way?
Right. Yeah, that's actually a good point. You could think about something like Jupiter, where it's 120 Kelvin or something like that. If you're operating at those cooler wavelengths, you could potentially detect and characterize Jupiter if you have the right wavelength range. It's all about determining the wavelength coverage that you have and figuring out which science you can do with that coverage.
We've got time for one more question and then one online question. Oh, okay, go ahead. Put me on the spot.
For a non-transiting planet, especially at like a distance of Proxima Centauri, is there a challenge of actually observing, like knowing the position of the planet for actually observing?
Right. So with this method, we're not resolving the planet from the star, so we don't need to know where it is. We're collecting simultaneously the flux from the planet and the star in a single PSF. So you don't even need to resolve that. But what you would probably do is observe the system over several orbits. So the orbital period, let's say it's 2 weeks, just for example. Maybe you observe it over 6 weeks, so you can get 3 full orbital periods to measure the variation in the planet's flux as a function of orbital phase, and then actually say make something meaningful about weather, right? I mean, that would be really exciting to say, yes, we detect weather variations on the planet's clouds, storms, whatever the case may be.
All right, I've got one online question. Other than the fact that people love from Michael Warner, is your sensitivity set by this diagonal background or by stellar shot noise? If the latter, this can be done in a light bucket mode with a telescope optimized for longer work.
Again, we've done calculations for ZODI, and we can actually resolve the ZODI as a third component. We have the planet, the star, and the ZODI. And as long as our exo-ZODI models are sufficiently precise and fortunately non-varying in time, we should be able to pull that out as a different feature. So we are, in fact, shot noise limited.
Thank Kevin again.
this time. Oh my God. An extra step required for this one. Almost. Let me go forward and backward and slide it. Okay, you're good. All right, next up we have Mandel from
Yep, thanks. And thanks for having me present this. And this is really a tag team, obviously, as you could tell from Kevin's presentation, with Kevin providing the introduction about the planetary infrared excess technique. And my presentation really diving in and focusing on the type of instrument requirements that you have to actually achieve the pi measurement on ProxMB and similar systems, but also thinking about reference missions in 18 months of observations. How many different planets could you observe? What are the types of those planets? And then finally jumping into the actual details. We've done initial instrument designs for the near infrared, mid infrared simultaneous spectrometer that would be needed to do this type of work. So starting again with this plot that's so powerful about the known M-star planets within 20 parsecs. The key here is that all of these are around the brightest M-stars that we know of. And so what that does is it means that a more modest aperture, 2 meters versus 6.5 or 10, could actually gather enough photons to actually get down to the limits in the mid-infrared that we need to detect this. And in fact, these are the primary targets that we'd be focusing on for this type of science. But as Kevin pointed out, the non-transiting planets cannot be examined by any existing mission or planned mission on the books. You require that simultaneous near infrared down to something like 3 or 2.5 microns, and out to 16, 17, 18 microns in the infrared at the same time, simultaneously. And no observatory can do that at this time. So that leaves open this fascinating area of science work for the next FAR IR probe mission. So I wanted to point out here, and I think Kevin mentioned this, that we're hoping to submit this paper next week, very soon, ASAP. So please don't spread these wonderful plots. We think they're wonderful about what we could do for ProxMB in 100 hours of observations. But this is, again, showing what you could do if you integrate over time. So 100 hours is about a quarter of the orbital period of ProxMB. And if you just integrate up all of the observations over time, you build up enough signal to noise to detect the O3, the CO2, and as well as H2O features out to 18 microns. And so this is what Kevin demonstrated. You can really get a fantastic grip on the atmosphere of this potentially habitable planet around the nearest star in a very short period of observing time, in a sense. So we call this the total integrated emission measurement to gather bulk diagnostics about your planet. But the really fascinating thing is if you have enough aperture and you can actually slice your orbital period of your planet down to get enough signal to noise, you can do a much more interesting, fascinating measurement of the thermal emission from a planet as a function of its phase as it goes around the star. And so now you're actually able to map, this is a map of water vapor for the planet WASP 43, which is actually done by Kevin and his team back in 2010, I think. I don't know, I dropped in 2014, excuse me, with the Hubble Space Telescope. So you see this very short wavelength region. We're proposing essentially to do the same exact thing out into the mid-infrared for habitable planets around the nearest stars. And so this type of mapping, as Kevin said, is even beyond the capabilities of what LUVOIR could do without extreme amounts of exposure time for planets around the nearest G stars. So we're really proposing to jump the gun here on what we could do for mapping the surfaces and atmospheres of habitable planets. So we then went through the process of actually looking at several different mission scenarios. The first one, we assumed that we would just do essentially a survey of all of the planets known from radial velocity detections from the ground, and this is an ongoing and increasing effort from the ground to detect all the planets around the nearest M stars. And so these are the known planets we looked at based on signal to noise, spectral type, size of the planet, the magnitude of the parent star, how many planets we could actually survey in an 18-month period with a 2-meter aperture telescope, since most missions are looking at that. You can see that we can do a really excellent survey of around 40 different planets spanning all the way from 200 Kelvin equilibrium temperature all the way up to 700 Kelvin. So we're spanning essentially Venus all the way down to, to Mars or outer habitable zone planets, both rocky and Neptune mass planets, essentially. You can see up to 20 Earth masses around the nearest stars. So we're probing the size and temperature of planets that really we only have a few targets that JWST could do. Kevin mentioned TRAPPIST-1, which is the canonical system with Earth-like planets. That's essentially the only system that really we can do potentially habitable planets with JWST. This would allow us a true survey spanning a range of equilibrium temperatures. And then if we actually look at phase curves, where you're actually mapping the day, night, and quadrant and morning and evening quadrants of the planet, you could actually do about 24 planets in 18 months. Of course, the balance of what you would do depends on your survey, on your focus, your science focus. But of course, these take a lot more exposure time. So your exposure time limited within the 18 months versus here, where you can see you're down within the 10 to 20 day period for most exposure time for most of your objects. And you're really sort of background limited, as in the objects get too dim and the background, the ZODI, solar system ZODI background becomes limiting, which is related to actually what Mike Warner's question was. So we still have enough targets even without being ZODI limited. And again, this is the potentially habitable regime. Many planets, both Earth size and Neptune size in this regime. Okay, so I want to lay out the telescope and instrument requirements, because you'll notice that my main point about laying this out is this fits very well within the parameters for most of the potential far IR probe concepts. Telescope less than 35 to 45 Kelvin, depending on your aperture. So that's easily met by most of the concepts we've heard today. Minimum 5-day continuous pointing window is enabled to be able to get the signals to noise you need for one pointing on an object, 4 to 5 days, 100 hours in a sense. So at L2 or other types of long, cold orbits, this could be met. This actually thermal is related to this telescope requirement. Simultaneous spectral coverage from 2.5 to around 17 microns, 18 microns if possible. We already talked about how 3 microns to 2.5 microns is the short wavelength cutoff for a number of missions. Less than 5 parts per million post-processing noise floor over 25 hours. And this is the one that's sort of less intuitive for people to kind of understand. And I'll go into that in a sec. And then high throughput at long wavelengths, so you can gather those mid-infrared photons from your planet, but moderate to low throughput needed at short wavelengths, where your star, a bright M star, is dominating your spectrum. So these are the basic requirements of what we need to do this type of work. So a note about the idea of noise floor. A lot of people get worried when we say 5 parts per million, stability of your noise floor. What we're really talking about is what's been demonstrated with the Hubble Space Telescope and soon to be the James Webb Space Telescope, is the post-processing or detrended noise floor of your instrument. So here on the right, I show this classic paper by Zach Berta Thompson et al. In 2012, showing these are the systematic essentially variability of the WIF C3 instrument on HST. This is the repeated every orbit. It shows these ramps and other variability within each orbit. But there's many detrending techniques that can get us down to essentially a white noise residual sort of noise floor that's far below the variability of the detector and instrument itself. But the key is that you need strategies to calibrate out what is the instrument and what is the stellar or planetary effects themselves. And so by monitoring the change in wavelength dependent sensitivity and the variability in the SED at short wavelengths of the stellar SED, we can mitigate these instabilities in the instrument and easily reach this required noise floor. So key instrument technology. That we're baselining this detector, this H2RG detector doped to work at long wavelengths through work by University of Rochester for the NeoCam mission. Many people have pointed out that these new detectors as baseline for NeoCam work out to 15 microns, and even one of them has been demonstrated to work out to 17 microns, which is the one that I highlight here. This is work by Mario Cabrera, who works at Goddard and worked on this for his PhD work. High TRL, obviously, H2RGs, large format, sophisticated readout schemes, but obviously there are challenges. One of the main ones is dark current. So you really have to get this detector down below 25 Kelvin at the focal plane array to get down below 100 electrons per second in dark current, which is what we need to reach the noise limits that I showed before. And finally, we need to essentially be able to measure the sensitivity of your instrument to detrend the data from instrumental variability over short to long time scales. And so we at Goddard have developed a number of control mechanisms and calibration strategies, which I have left to the backup because it gets into some details. This work has been done by Johannes Dagun. Of course, many people know Johannes and our team at Goddard. And it's already being tested in the lab right now at Goddard to be demonstrated in the future. So this is the basic idea, is that if you have a 2-meter telescope, you have this very small, simple instrument with 2 wavelength channels essentially laid out on your H2RG detector using a short wavelength and a long wavelength channel with 2 different dispersing elements and resolving powers of between 90 and 170 that could be binned up down to R50, which is the resolution we need for Earth-sized planets, or is optimal for Earth-sized planets. And so it's really a simple high TRL instrument, no moving parts for this, and could easily, sort of squeezed into the instrument suite for a range of different types of mission concepts. The impact of telescope surface roughness. Now, the key thing for all of these far infrared missions is this question of what will be your actual, availability of short wavelengths. First of all, are you diffraction limited? And for all of this work, we've assumed diffraction limited at the longest wavelength of 18 microns. And so that defines how much ZODI background you have coming into your aperture, right? Because you need to get outside of essentially your PSF in order to not have slit losses. So we don't need a strong diffraction limit, and that's because the stars are so bright. We don't need a very short, small sky window that we're absorbing because our stars are quite bright. We do need throughput, but we've shown with a calculation of surface roughness that if we can get down to at least 50 nanometers, we can get high throughput all the way down to essentially 3 microns and moderate throughput at 1 micron. And so this 50 nanometer surface roughness should easily meet the requirements for throughput that we need for our light bucket science case for this instrument. So just summarizing here, essentially, the Miracle primary science case is unique and compelling. I think Kevin's talk really demonstrated that we would really be breaking open a whole new area of the study of the search for life on other planets. And 2-meter and above apertures could really allow us to do mapping of the atmospheres, both vertically in the vertical direction through the thermal profile, as well as through longitudinal mapping of phase curves. There's also many other secondary science cases. Many of the missions have already thought about mid-infrared science cases for spectroscopy. Brown dwarf mapping, which is already being done with HST, and soon James Webb could be continued simultaneously. Supernova, GRB follow-up, solar system monitoring, mapping, and lots of other things that you in this audience might be thinking of. The instrument is compact, relatively simple, with high TRL components already demonstrated and about to be demonstrated to the required performance. And finally, it fits with almost all of the far IR probe concepts if they if the concept is allowed to at least address some of these basic requirements for temperature, surface roughness with the telescope. So I'll leave it there. We're really open. Our team right now is myself, Kevin, Johannes, and a number of other folks at Goddard and APL. But we're really happy to discuss more about how we might be able to make the Miracle instrument fit within your concept. So that's it. Thanks.
All right, good questions.
Hi, Gary Miller. I love both talks, but I have a question about confusion. Obviously, your beam will be taking in an entire system, which may consist of known planets and undetected planets by either the transit or radial velocity technique.
Yep.
How do you interpret the data when, in fact, examples, if I understand them, sort of assume the addition of a single planet and your interpretation of that single planet, when in fact there's a probability, a non-negligible probability, that your beam actually encompasses multiple planets?
It almost certainly will if it's a combined light measurement. So it will encompass any of the planets within the PSF that we're measuring. So your point is very well taken, and that's a key strategy. Kevin pointed out the 3 axes of differentiation, right? And the key one to handle that problem is combining the time axis with the wavelength axis, because we know the periods of the known planets very well. We know when they are moving around the star, and therefore you will see a thermal variation from those planets on that exact orbital period. The day side will be somewhat brighter than the night side in this sense. Second of all, the planets that have the higher thermal contribution because they're hotter will be the ones most likely to be detected by radial velocity because they're closer to their star, moving quickly, having a larger gravitational effect. And finally, you'll be able to look at infrared contributions that don't vary at all, essentially over time, and compare them to the stellar SED that you would expect and see if there's additional non-varying components. So these challenges are real, but I think that as we move towards the 2030s and we better characterize the planets in these systems, and we understand essentially new ways to differentiate between these, we will be able to handle these most scenarios.
Is it fair to say that you may have greater difficulty with systems that are closer to face on than head on?
Systems that are close to face on, we will have almost no ability to actually map their thermal variation. But those are the systems that wouldn't be detected by radial velocity.
That's my point.
Yeah.
Is that you can't take out that variation if you don't know.
Exactly. So those are not included in any of the essentially the target list that I baselined here. So yes, those would be almost impossible. I mean, not impossible. We can think of some new strategies to try to differentiate that.
Thank you.
Do you have any other questions? I have another question for you.
Yeah.
Go back to the surface roughness. So for your short wavelengths, this is not just throughput, this is what you're losing before it's scattered.
Yeah.
Your radiation shields.
Yeah.
That is going to introduce time variable for the short wavelengths that are important for measuring stellar flux. How do you think that impacts measuring process?
Yeah, that's an interesting point. I think that we'd have to evaluate that through the design of the actual optical path and try to understand if we could essentially mitigate the scattered light either through filters or designing the optical path. It's a great point. If those photons have to go somewhere, and we have to think about how we can mitigate that. It's a great point.
I apologize to everybody for all of that. I'm just, since, this is my first time looking at this, I'm just brainstorming a little bit, and I was wondering, could you do something, there's lots of people it's more of a difference measurement where you had some reference.
Yeah.
You know, reference stars more on board and maybe an FPS or something like that, if you're looking for the excellence.
Yeah, so we have a number of strategies to sort of think around that problem. One is this onboard calibration. So our instrument design uses this idea of a thermal black body around the same temperature of the star, different from your planet. So you could actually scale and essentially recalibrate your instrument and the wavelength dependence of that sensitivity using that. The other idea is to find a couple really good naked M stars and try to essentially do the same work on them first or as part of the mission in order to calibrate and understand how the star will vary and change. It's not the same star. There's always going to be some uncertainty, but those types of things, which could be built into any mission and instrument design, would really help with these questions.
Okay, I think I'll be one of them.
Thanks.
Now we're going to move to today's large group workshop session. I don't know who's going to lead this. Let's bring up the slides so we can figure that out.
Gonna point at Mike.
First, I need to find them.
I assume we'll do the same thing as we did yesterday, basically, although in a much shorter time. So we're gonna have to be rapid fire on our debrief. We all are going to go not be here and talk about science someplace else. So I suppose if people want to come and whoever is presenting for each of the groups, yeah. Who's group one?
Come on up to the Price is Right. Oh, if I can find it. Blind.
So maybe I propose we do all five and then open up for discussion until we have to go.
Yeah, I like that plan. So maybe each person from groups 1 through 5 who's going to present their discussion should come on down to the front of the room. That way we can really do this rapid fire.
All right. Good one. Go ahead.
Okay, so for group 1, our question was what science could be done by a probe size mission that would not be possible with smaller space, suborbital, or even ground-based programs. I would imagine the answer to this question would be very long, but in the limited time that we have, we focused on the science spaces. There were a lot of discussion about the technologies that can be done only with the budget for a probe-sized mission, but we didn't include them here, so we just focused on some of the science spaces that requires a probe-sized mission. So the first one, anything probing water spectral features, such as protoplanetary disks, they need to be from space. Sophia Hermes can do about 20 to 30 objects, but if we want to go to fainter samples, we need space. Faint objects, if we want to observe anything that is faint, we need bigger apertures. This includes lots of science, including disks, ISM, galaxies. The third point, we need probe-sized missions for if you want to observe general population of galaxies beyond the local universe. If you want to study their dust properties, the obscured star formation, abundances, AGN activity by probing their dust emission in infrared, gas emission lines in the infrared. And this is particularly for cosmic ring galaxies where ALMA is not probing the same wavelength. We need probe-sized missions in space. Science cases that need statistically large samples, they need big apertures for fast measurements, large field of regard, longer mission lifetime, and longer mission lifetimes to gather more targets. The budget for a probe-sized mission would enable us to get more instruments on the same platform, make it more capable, make the telescope more capable and enabling better discovery space. And then the last bullet point, time domain monitoring or alerts, they need to be continuously available, higher readability, fainter objects, high resolution. All of these need probe apertures. As an example, stellar accretion in far infrared, these long baselines or exoplanet phase curves are science examples for this point. Thank you.
All right, so our slide doesn't look as friendly, but I was just taking notes. So broadly, our question was, so the X-ray probe gets selected, so FIR has to wait another decade or so before you get your probe. So what do we do in the meantime? So we have three broad categories that we focused on. One, of course, we look at what other platforms are available. So SMEX and NIPS, of course, but of course there's a very limited number of those over the course of a decade. You can do great science with that, but there's not that much of that. Pioneers, balloons, and sounding rockets are starting to be very low in terms of what you can do with those. Sounding rockets and balloons especially have been challenging for the far IR community, because if you want to keep things cold, cryocoolers are pricey, to say the least, and they're also large. You can't put as much technology on these things. The second thing we focused on was tech development. I know they're shutting down Sophia, but maybe we could keep the plane for a test bed was something that came up. We can continue to improve detector technology. Ideally, we'd love to get some low background test facilities built so we can start to test our detectors and up the technology readiness level before we're putting them on space missions. And then finally, something that came out of that worked really well with the Origin study was that there was a monthly group between the different tech dev teams where they were talking to each other, which kind of brings us into the third category that we had was generally broadly community building, both within infrared and between infrared and other parts of science. So we thought about maybe having some sort of summer school for infrared. Aspen Center for Physics is close by here, and they do great stuff. It'd be great if IPAC stepped forward and helped be some sort of coordinating body for the community. And then we also wanted to try and build more interest out of the field. There are challenges in trying to work with planetary and Earth in terms of you start to put other things on a mission and people are like, well, that's not astrophysics, so we don't want to fund them. But hopefully that we could maybe break some barriers with that and get the different parts of NASA to work with each other more. And then likewise, there is some prep work. If an X-ray probe was to move forward, that maybe we could help them in some way by doing some infrared work that would choose targets for an X-ray thing, or likewise, the X-ray probe could maybe do some work that would then prep for the far IR probe in the future.
Thank you. IRSTIG will have 3 points to person.
You guys are doing great.
Okay. No, you're fine. Hello, I'm Jessica. I am a postdoc at Sophia, and I'm going to do my best to represent what Group 3 discussed, but might miss some points, so please be patient with me. So our question was, in order to maximize scientific return, how should the probe mission concept balance surveys versus general observer science? What is the science trade space and how do we optimize return? And so can we start with just some kind of background thoughts of what we should be considering as we discuss this question? And so probes will likely, the first thing was that some of the survey projects will likely be geo-led, so they're not necessarily, there's some caveats to this question. There will be a lot of JWST data collected before the probe flies, which might help determine what types of surveys you want to do. Surveys can be beneficial because they have nice, well-defined parameters and uniformity, which can allow for archival science that can be more difficult with a broad range of geo programs. But GTO surveys and GTO surveys tend to be small because they're spread over many people and only compromise 15 to 20% of the time. But the nice thing about geo projects is that they can, help bring in more of the community. They can give funding to people who maybe aren't the biggest names, and they can diversify the types of science we're doing. So there's benefits to both. And these are just some of the things we discussed. And then there's a second slide, which we can, thank you. So some ideas about how we might want to optimize is that maybe we want to do surveys and then follow up on interesting targets. There was a lot of discussion about bringing in the community early on. So I think this is something I benefited from the early career PRIMA workshop last Friday. So early career scientist PRIMA workshop last Friday, but like getting the advice from the community early in the design process, which I think is something that is happening here. And it's great, we're seeing that in all of the probe missions. And then I've been kind of like focused on this community idea was that there's an issue with some of the like HST models that you see the same groups getting time repeatedly, and therefore kind of they're the ones that get funding, and they're the only people who can hire postdocs, and that can kind of limit what the field is doing and make it harder to bring new people in. So kind of thinking about, as we design this, making sure that we're using Geo Program as a way to grow the community, and that might mean that there's lots of, again, early community participation, and then lots of also training for people who maybe haven't worked in far infrared before, whether that's tutorials or workshops or whatever else. We also discussed a little bit about funding for archival work if there is more of a focus on surveys. So something like the Roman model, which I know less about, but making sure that there's lots of archival funding for people to investigate those. And then that also that the best method might depend on a probe class that is selected, or a probe mission that is selected, where Spirit might be best with kind of more pointed geo, and might be better suited for more large surveys. So I think that is our major plans.
All right, hello, my name is Jeff McKinney. I'm a grad student in Mass Numbers. So Group 4 had the easy task of figuring out how, after ultimately one probe class mission is selected, how do we foster unity as a community throughout this process, and then be able to move forward cohesively. So we first kind of began by reminding ourselves of this really central goal, which is that we want the far infrared probe to win over the X-ray probe, and we all have vested scientific interests in that happening. And then we were trying to use that to branch out and figure out how we could reach this goal and keep the community sort of nice and tightly bound. There were discussions of positivity and having the right mindset, but then we definitely wanted to emphasize those. Then we also focused on coming up with like concrete, actionable things that we could kind of put together or organize. Something that came up as like a general theme was building in early transparency into all of the concepts. And so this could be information sharing, which has been done through fact sheets already, which is great. But also if papers are being written that are preparing different technologies or science ideas, and then maybe inviting people amongst this community here to join those papers would help foster future work together. Obviously emphasizing everyone to join all the teams is a great step forward. And then if there are technical tools that are in development to predict sensitivities or integration times, and sharing those broadly would also help bring people in later down the line. We also talked about what it might look like bringing the community together after stage 1 selection, and maybe having like a similar workshop like this, but perhaps maybe virtual or piggybacking of other established workshops or meetings. This was already talked about in one of the previous questions, but we also thought that standardizing a Geo program across the different calls would help give people expectations that they could apply to different probe concepts. Yeah, but again, there might be nuances there depending on the scope of each mission. And then we also wanted to remind all the probes to identify key science links to all of the different goals outlined in the decadal, because that's obviously going to be a good way to access a wide source of the community. Thanks.
I'm Dave Chus. So our group had to discuss how might a far infrared probe mission most influence the science case and design of a future flagship mission. And then how would this fit into the broader mission landscape and complement suborbital platforms? So we took this to mean, thanks to Mike's guidance, that the LUVEX was the flagship mission this is talking about here. And we identified, it was a pretty tough question because of a couple things. The design periods of far infrared probe mission would, if it were the first one selected, would certainly overlap somewhat with LUVEX. And of course, with the second one, it probably wouldn't influence much at all, right? In many ways, the far infrared probe would be really orthogonal to LUVEX, but there are certainly cases where data from these would be nicely complementary. Just kind of skipping ahead a little bit, I'll come back to the other point. One of the things we cited as an example of such a synergy would be that LUVEX would look at, in terms of exoplanets, LUVEX would look at more mature or protoplanetary disks specifically, would look at more mature planetary systems where dust extinction might be minimal, whereas far infrared missions start to understand chemical composition as function of radius, but together these things can have nice synergy to kind of fill in the big picture. Let's see. So the other thing we identified was that JWST would have probably more influence on the design of LUVEX than the far infrared probe. So there are other couple of science cases where, such as extragalactic science or the rise of metals, where these two things could overlap as well. And then finally, how would this fit into the broader mission landscape and complement suborbital platforms? So some of the science can be done, pieces of the science can be done from suborbital balloon platforms, particularly. Specifically, niche science cases could be found that would be more limited than the space missions. These would be kind of things that might be able to be picked off where particular techniques that might have less of an advantage of space than others would be good targets for balloon missions, particularly. I'll end it there, and then I'll open up for overall discussion here.
All right, thanks to all of our speakers again. Before we go into the discussion, just to remind everyone that that's going to be here at 5. We want to be on it basically immediately. So we have
22 minutes.
22 minutes. We need a little bit of time to have everyone pack up and make their way to 30 yards to the bus outside. So just keep that in mind. All right, Matt, go ahead.
And just a little bit, one point of clarification. I think that surveys could easily be a general observer program as well. Surveys are not really necessarily about the PI. So I think the point of these probes is the geoscience. I don't think people will disagree with that. But science seems kind of facilitating that. That's what we should think about this. We live in a greater territory there, basically. Right? What about that?
Well, just a general remark. I'm getting the sense here that a lot of people have the impression that Sophia is dead. I should really emphasize, Sophia is performing way better at this point than the period the cable survey referenced. So we have a fully functional, well-performing observatory. And I just want to put this here, so it's not that, okay? It's a proposal.
Okay, so I know some of us are leaving tonight for various reasons, and so they won't be here tomorrow to talk more about the probes. So if you are a person who's leaving tonight, now's the time to give us your thoughts. Bill, George, George will go.
I am actually leaving tonight. So my big picture thought about was something that someone brought up, maybe one of these, or actually several of these slides, is this need to bring in the rest of the non-far IR community to the excitement of far IR in that sense.
So, and frankly, the same is true for the X-ray probe. Is I think finding ways to make sure that we are reaching out and advertising all of the great science that FRI are available to across all of astrophysics, planetary science, is a key aspect if we want to really make sure that it does get selected, hopefully the first time. I'd love to hear more ideas about how we can do that.
Well, George from Allman, not George Wells, I guess, but when I give that to Meredith and Ariel, talk about doing a webinar, science focus. So I think that's an important or easy way to bring people in, is to have a science focused set of talks, webinars, even conferences, really hammering on what the FAR can do. So that's one easy implement project that we talk about doing this summer or this fall. So if you're interested in that, I guess talk to Meredith and me. So gearing up for an IR probe, something that we should look at are some really new experience simulations that are beginning to move their radiation transfer calculations into the infrared window. This is sort of a new space that's being explored in at least high spatial resolution galaxy simulations as the need to understand dust and its production rises. So maybe we can link up with theoretical communities and in particular help use those simulations and those new radiation transfer calculations to make some of the synthetic observations that we can go wait around, say, look up for you.
Okay, one comment and then a general comment. So if you do a webinar series and stuff like that, if you want other communities to join you, you probably have to have people from other communities on your panel or your webinar or going back to the geo science, it sounds like most of these probe studies want to do some sort of geo program. I think that's important. That's a really good thing. It will depend on what type of capability it is. So, I was looking at APEC yesterday about Nancy Grace Roman telescope, and everything is a survey with that. It's just what it's built for. So it probably depends on just what it has to offer. But if you talk about a geo program that you can do a survey, and the survey might be only an hour. Or you have pointed observations, and your survey might be a bunch of pointed objects. I don't think in our session when we were talking about geoscience that it had to be targeted like a whole lot, because that's what people are most familiar with. I think we can broaden that out and also look at archival funding and seeing a way of doing geoscience. It could be your idea of what you want to do with the data.
Dominic is offered some wisdom. Hardly wisdom, but I think I'll sort of riff on what Martha was just saying. I've heard a lot about Geo and how valuable it could be for a probe, and I wanted to suggest, from my perspective, that something that would be useful is if people who here in the audience are familiar with the, say, the recent mid-X call, I've been on a proposal or considering one, and you've read that and you know what the policies were written there, and how Geo in mid-X tends not to be very emphasized, but it's probably very emphasized in the probe. If there are clear policy choices that we could make within the NATO that would allow you to put your best foot forward, please think about those things, write them down, email them to Pat Knesek and CCB, so we can make sure that we think about those things as we're writing. Just take as an example that the mid-X is the way we're going to implement this. If we're getting it wrong, tell us now. We can fix it before we get too far down the road, and then you can plan for it in a way that, as Margaret says, makes sense for the mission concept you're developing. It doesn't have to look like Hubble. It has to look like what makes the most sense for your science.
We are talking about probes on this one, but there are all these other small flight opportunities. I have a bit of worry that at least here at the meeting, we are not using so much time on thinking through what those smaller opportunities are. Yes, focusing on the probe is a good idea, but there's a limited chance to get it. If we spread out when we over those smaller missions, we have a higher chance of hitting. And obviously, people will do that at home in their home institution, but that is still one activity we should also spend some time on here at this meeting. So not only focusing on this one big opportunity.
Okay, all I'm going to say is here on that. Well, I'll say more, but I agree with that sentiment. And I was going to say, I think we can be more ambitious, maybe, in our thinking about, far infrared possibilities. I would encourage all of the thoughts that's going into the probe mission, that we not thinking about it. I didn't like the phrasing maybe the question, but what if a far infrared mission isn't selected? But thinking about, even if it is selected, what else can we, leverage, and what other things can we do that are based on all of these studies? Because not all of the probe missions will be selected for, even if one far infrared one is, but there'll be other ones that won't be. And then, small formation flying or small, interferometry or small community crowd. Anyway, I'm not going to ramble on, but yeah, let's do more ambitious.
Yeah, just in the spirit of these small ambitions, there were along the years, there were these ideas of, for instance, there was a mission concept called H2X, looking for molecular hydrogen. There's another possibility looking for polarization in the galactic plane, for instance. I mean, think about these highly specialized small telescope ideas that could be realized in such a concept.
We have to go down a few more minutes. I think it might be probed out there. Margaret?
So just to follow on Jens's thought about the small missions, I mean, I think the focus today was on the probes, but I think it is important. I mean, it's this wavelength range has so much discovery space. You can do something with a small experiment and find something new. So I think those small things are worthwhile. And if we could, if there's some kind of coherent roadmap with those small things also help push along some of our bigger objectives, because there is the DAO did call out a technology maturation plan. Aligning and coming up with small cool science, but there is a lot of cool science you can do with very small effort because of this discovery space.
You time for another comment or two. Maybe we're done. The natural. Oh.
And this is probably a question for Dominic, but listening to the probe concept, it's considerable. There's international participation in almost all of the concepts. So would the probe line follow the same kind of rules that international contribution on a NASA mission work, such that you can't have an international contribution needed for minimum mission success in case the detectors were delivered in time? Or is this an opportunity to change the paradigm and realize that our European and Asian colleagues have some technology that we can share together to push forward this discovery space technology would do that. I mean, anyway, that's international.
Well, maybe I should try to answer that. Thanks for the question. In the draft AL, I don't know if we've gotten to that yet, but in the community announcements, we did not purposely, we did not say that you couldn't have required things. If you look at it, you can see that a foreign contribution could include, for instance, things that are essential for the spacecraft bus, like let's say your solar panels could come from international contribution, in which case it would absolutely be essential for those things to work. That's not precluded. So it doesn't have to be merely active on. The only limitation is the scope, because we want the US contribution for both the science payload and for the overall investigation to be the vast majority. No more than 1/3 of this additional contribution. So essentially, from a foreign agency, or a combination of them, no more than 1/4 of the value. And we're trying to calculate the value.
All right, maybe that's it. Well, thank you, everyone. So this is about to close. Truck is outside. Those of us who want to go to Speartown and don't want to drive, it's a very reasonable thing. Still reading. But we're going to ride the bus. 56 of us. All of us want to go and I'm sure that there are most of the drivers with people who yeah.